Welcome back. In this video, we are going to solve problem 6-142 that is taken from chapter number 6 bending and book name is Mechanics of Material by R.C. Hibbeler 9th edition. And the topic is curved beam. So statement is if the maximum bending stress at section AA is not allowed to exceed 150 megapascal, determine the maximum allowable force that can be applied to the end of the beam. So you can see this is a curved beam, clear, and it is given that allowable stress should not exceed 150 megapascal at section AA, clear, and we have to find the largest load P that can be applied to this curved beam. So let's start with the solution. As we know that the formula that are used in curved beam is this one. This is for stress. This is E, which is R dash minus R1, R, capital R. So R dash is distance from the center of curvature till the centroid of this section. Clear, this will be R dash, and R, capital R, is distance from this centroid, center of curvature till the neutral axis, because in curved beam neutral axis and centroidal axis do not pass each other. So we'll find this term as well, and this R, capital R, can be obtained by using this formula. So we'll see them in a while. So first step is that if you cut this beam, curved beam at section AA, so I have already drawn the free body diagram over here, FBD. So you will have a shear force which will be acting upwards. So this will be V, which is VA dash A, and you will be having a moment which is equal to MAA. So we'll find this MAA by using equation of equilibrium, that sum of all moment about neutral axis must be equal to 0, taking the counterclockwise moment as positive. So about this neutral axis, the first moment will be this P into perpendicular distance is this 0.6 meter, and it is producing counterclockwise moment, so it will be positive. And at this we have a moment MAA which is clockwise, and their sum must be equal to 0. So I will write P into 0.6 minus MAA is equal to 0. So it means that MAA will be equal to 0.6 times P. We do not know P, so this will be MAA, which will be 0.6 P. Okay, now you can see this moment, and due to this force there will be a moment will causing bending moment in this curved portion. So as a result, this moment is this and this moment is this. So it will straighten up this beam, curved beam over here. So this top portion will be in tension, clear, and this bottom portion will be in compression. So we have to find the maximum load. So for that we will find maximum bending stress at this top as well as maximum stress at the bottom. This is for top and this is for bottom, and from this we will find the P value. Okay, now we have this moment. So what we will do is that we will find this term which is R dash. So R dash is distance from center of curvature till the centroid of this section. So this is the section, you can see section AA. So this is the center of curvature. So if I draw a horizontal line from center of curvature, so we will find this R dash. Now you can see this T section will be divided into two portions. This will be first portion and this one will be second one. Okay, so there are two rectangles. So we know that we have for these two rectangles, we have centroid formula will be equal to sum of y dash bar into A divided by sum of area. Now we have two sections, so y1 dash into A1 plus y2 dash into A2 divided by A1 plus A2. We will find this A1. So A1, you can see this total width is 75 millimeter, 25, 25, 25. So 75 millimeter is 0.075 multiplied by this thickness is 20 millimeter, which is 0.02, and the unit will be square meter. Now A2 will be how much? So you can see the height is 50, so 0.050 into thickness is 25 millimeter, which is 0.025, and the unit will be square. Now what is y1 dash? So y1 dash is distance from this center of curvature till the mid of this section. This is your y1 dash. So this is y1 dash, and y1 dash you can see distance from center of curvature till point A is 300. Radius is given, so half of 20 is 10. So 300 plus 10 is 310. So 310 will be equal to 0.310 meter. And y2 dash is distance from centroid center of curvature till the center of second section. So this is y2 dash. And this y2 dash will be equal to, let me show you, 300 plus this 20 and half of 50, which is 25. So 320 plus 25 is 345 millimeter. So 345 is actually 0.345 meter. Now you have all this value, just plug it in this formula. So r dash will be equal to y1, which is 0.310 multiplied by area is 0.075 multiplied by 0.02 plus y2 dash is 0.345 multiplied by area, which is 0.05 multiplied by 0.025 divided by sum of area A1 and A2. So A1 is 0.075 multiplied by 0.02 plus 0.050 multiplied by 0.025. Okay. So when you calculate it, you will get r dash will be equal to 0.325909 meter. So let me draw it. So it is distance from neutral axis till the centroid of this section. Lead centroid is this C point. Clear? So it will be the distance from center of curvature till this point. So this is r dash. Okay, r dash, and that comes out to be 0.325909 meter. Now what we will do is that we will find the second term, that is capital R. So capital R is distance from center of curvature till the point where neutral axis lie. And you can see this R can be obtained by using this formula, which is equal to A divided by integral of dA over R over the area A. What is A? So A is equal to total area of cross sections, which is equal to A1 plus A2. So when you add A1 plus A2, so A1 is 0.02 multiplied by 0.05 plus A2 is 0.05 multiplied by 0.025. So when you add them, you will get this area, and this area comes out to be 2.75 into 10 raised to the power minus 3 square meter. We have find out this. Now we'll find this term, integral of dA over R for the entire area. So that can be obtained by using this table 6.6-1, so where you can see in one column shapes are given, and in another column the formula for this is given. Since we have rectangle shape, there are two rectangles. Remember that this line is the line that is passing through center of curvature. So from center of curvature, the first end of this rectangle is at a distance of R1 and second end is at a distance of R2, and the width of rectangle is B. So we will start for first one. So you can see this is first one. So this from center of curvature till the start of first rectangle, this is the first rectangle. This R1 will be equal to 300 millimeter, which is 0.300, and R2 will be this one, which is equal to 0.320 meter, and width is this one, which is 75 millimeter. So I will write down these all values. So you can see the formula for this is B. So B for the first rectangle was 0.075, ln of R2 was 0.320 divided by 0.30. Now for the second rectangle, you can see this is the second rectangle. This is second rectangle. One edge of this from the centroid is this, which is 0.320, and that will R1 for the second rectangle, and R2 is this one, which is total height from the center of curvature, which is 0.345 0.37. Let me show you 0.37. You can see this distance is 300, this is 20, and this is 50. So 370. So R2 is 0.37 and breadth is 25 millimeter or 25 millimeter for the section 2. Okay. So write down its formula as well. So I will write B is 0.075 and multiply by ln of R2 was 0.370 divided by 0.320. Okay. Now when you solve this integral of dA over R for the entire area comes out to be 8.46994 into 10 raised to the power minus 3 meter. I will also represent this R. So R is distance from neutral axis till the point where its neutral axis lie. You can see this is its neutral axis, and this capital R is less than this R. This is capital R, which is 0.324678 meter. In curved beam, the neutral axis and centroidal axis do not pass. So you can see the difference over here. Now we have this. So you can just put in formula number 3, which is E is equal to R dash minus R. So R dash is 0.325909. You can see this one minus this capital R. We do not find R. So A is this one, 2.75 into 10 raised to the power minus 3, and integral term is this, divided by 8.46994 into 10 raised to the power minus 3. So R will be equal to 0.324678 meter. Okay. Now just put it in here, 0.24678. So you will get E is equal to 1.231 into 10 raised to the power minus 3, and unit will be meter. These are very lengthy problems, so you have to be very careful. You should not have any mistake. Now you have all this value. You can just use this formula. Sigma is equal to, let me write, sigma is equal to M into capital R minus small r divided by E into R. Now what is R? R is distance from center of curvature to the point where you find the stress. So we are interested to find out the maximum stress. So that will be in outer region and this lower region, top region and bottom region. So it means point A and C are our main focus. So for point A, R will be equal to RA, that will be equal to 300 millimeter, which is 0.3 meter. And for C, R will be equal to 0.37 meter. Okay. So first we will find for point A. So for point A, R is equal to RA, which is equal to 0.3 meter. And we have maximum, we know that allowable stress is equal to maximum moment into R minus RA divided by area into E into RA. We have maximum allowable stress is 150 megapascal. So what we will do is that point A is in tension. I will write point A is in tension. I have already told you about this. So this allowable stress will be positive. So 150 megapascal, so 150 into 10 raised to the power 6 is equal to moment. Moment is 0.6 times P, and capital R is 0.32467 minus R is 0.3 divided by area, which is 2.75 into 10 raised to the power minus 3 multiplied by E is 1.2314 into 10 raised to the power minus 3, and R is 0.3. So from here you can calculate this P will be equal to 150 multiplied by 10 raised to the power 6 multiplied by 2.75 into 10 raised to the power minus 3 multiplied by 1.2314 into 10 raised to the power minus 3 into 0.3 divided by 0.6 multiplied by 0.32467 minus 0.3. So when you solve this, you will get P will be equal to 10.292.09, or that will be equal to 10.29 or 10 raised to power 3 kilo Newton. Now this is the maximum load P that can be applied at due to the maximum moment at point A. For point C, I will write for point C, which is in compression, we have RC is equal to 0.370 meter. So just put it in this formula. Allowable stress is equal to M into R minus RC divided by A in E into RC. So moment will be equal to allowable stress multiplied by area multiplied by E multiplied by RC divided by R minus RC. Plug in all the values. So moment will be equal to allowable stress is, this is in compression, so it will be minus 150 into 10 raised to power 6 into A is 2.75 into 10 raised to power minus 3, E is 1.231 into 10 raised to power minus 3 multiply by this RC, which is 0.370, divide by this capital R is 0.32467 minus 0.370, and that is equal to moment. So moment is equal to 0.6 times P. I will replace this moment with 0.6 times P, clear? So that we should have, as we have less spacing, so 0.6 times P. If you divide 0.6 on both sides, so you will get P will be equal to, and solve for P, so you will get P will be equal to 6911.55 Newton, or that will be equal to 6.91 kilo Newton. So this is the value of load for the maximum stress at point C. Now you have two value, one is this one and another one is this one. So you have to choose load that will be lesser. So 6.91 kilonewton is the amount of load that can be applied to the point E. This is 6.91 kilonewton, which is the answer of our this question. Why we are choosing the smallest load? Because you can see this is satisfying this condition. So when you put this load, P is equal to 10 point in this equation, clear, in this equation. So it will exceed the allowable stress, which will cause failure. So we will choose this smaller load, which is 6.91, that will satisfy the condition. And that was all about this problem 6-42. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve example 6.14 that is taken from chapter number 6 bending, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the member having a rectangular cross section in figure 6-28 is designed to resist a moment of 40 Newton into meter. In order to increase its strength and rigidity, it is proposed that two small ribs be added at its bottom in figure 6-28b. Determine the maximum normal stress in member for both cases. So you can see this is figure 6-28, in which there is a rectangular cross section and that is used to resist movement of 40 Newton into meter. And in order to increase its strength and rigidity, two small ribs, these are the small ribs which are added to this rectangular cross section in order to increase its strength and rigidity. So you have to determine the normal stress in member for both cases. So we will find the maximum normal stress for this case A and maximum normal stress for this portion B. So let's start with the solution. First, what we will do is that for case A, that is without rib, so without ribs, we will take this figure A, clear. So without, we know that maximum normal stress is equal to moment multiplied by C. C is the maximum distance from neutral axis divided by I, clear. So we will find this moment of inertia I. So how we will find this I? So as we know that moment of inertia for rectangular cross section is equal to 1/12 base time height cube. As you can see that if you take the mid of this vertical line, clear, and the mid of the horizontal line, so it will coincide at this point, and this point will be centroid and neutral axis passing through this centroid, and the moment is 40 Newton into meter. So its breadth is 60 millimeter and height is 30 millimeter. So I can write this 1/12 base is 60 and 60 is equal to, in meter it is 0.060 meter, and height is 30 millimeter. So in meter it is 0.030 meter, and we will take the cube. So when you solve this, you will get moment of inertia will be equal to 0.135 into 10 raised to power minus 6 meter power 4. Now you have this I, and you can see C is the maximum distance from neutral axis till top. Since both top and bottom are at the same distance, that is equal to, you can see 30 divided by 2. So this distance both are equal to 15 millimeter, and that is 30 divided by 2. So C is equal to, I can write 15 millimeter, which is 0.015 meter. Now you have each and every value, so you can just plug it in this. So you will get maximum normal stress is equal to moment. Moment is 40 Newton into meter, and C is equal to 0.015 meter divided by I is 0.315 into 10 raised to power minus 6 into 6 meter power 4. So when you solve this, if I want to write the unit, so you can see the unit of 40 is Newton into meter, multiplied by C unit is meter, divided by meter power 4. So you will get the answer is equal to 4.44 into 10 raised to power 6 Newton per square meter. And in mega, you can also write it 4.44 into 10 raised to power 6 Newton per meter is Pascal. So in megapascal, it is 4.44 megapascal. So this is the value of maximum normal stress for rectangular cross section shown in figure A, that is without ribs. Now what we will do is that for with ribs, as you can see, two small ribs are added at the bottom. So what I will write is with ribs, that is figure B. So as you can see that two small these ribs are added at the bottom. So if I take the mid of this, it will be not symmetrical about. So its centroid or neutral axis will be not at the mid of this 30 millimeter. So what we will do is that first we will find the centroid or the location of neutral axis. That can be obtained by using this formula. Y bar is equal to sum of y dash into A divided by sum of area. And what we will do is that you can write it as, if you take this whole rectangle as one unit, this whole rectangle without rib is 1, clear. So its area is how much its area will be equal to 30 multiplied by this total length, which is equal to 10, 10, 10, 10, 40, 50 and 60. Clear? So its area, let me call this, let me draw it, let this rectangle which I have drawn as blue is taken as 1, and this we can write this formula is y dash 1. So y dash 1 into a1 plus, you can see there are two small ribs at the bottom, both are same dimension, and we called it as 2. So we can write this formula as plus 2 times y2 dash into a2 divided by sum of area. So area for a1 is a1 and 2 times a2. What is area a1? So we can write area a1 is 30 multiplied by total length. This length is 60 millimeter. So in meter it is 0.03 multiplied by 0.06, and the unit will be square meter. Clear? And what is y1 dash? So y1 dash is distance from the reference line till the mid. So we will take this top surface as a reference line. So from reference line till the mid of this first section is this one, and this distance is 30 divided by 2. So this is y1 dash, and that is equal to 15 millimeter. So y1 dash is 15 millimeter or 0.015 meter. Now what is a2? So a2 is, you can see this small segment. So its height is 5 millimeter and width is 10 millimeter. You can see 10 millimeter. So I can write it, height is 5, so 0.005 meter into 10 millimeter, and 10 millimeter in meter is 0.10 meter. So it will also in be square. And what is y2 dash? So y2 dash bar. So y2 dash is distance. Let me zoom it. It will distance from this reference line. Clear? This is the reference line. So distance from reference line till the mid of this section A2. So this will be y2 dash. Okay. I will also unzoom it. Okay. So y2 dash is equal to this 30, and the half of 5 is 0.25. Clear? So that will be equal to 2.5 millimeter. So 32.5 millimeter. Okay, and this 32.5 will be equal to 0.0325 meter. Now you have all the values, just plug it in. Y1 dash is 0.015 meter into A1. A1 is 0.03 multiplied by 0.06 plus 2 times y2 dash. Y2 dash is 0.0325 multiplied by area A2, which is 0.005 multiplied by 0.01 divide by sum of areas. So sum of areas is area A1 is 0.03 multiplied by 0.06 plus 2 times the area of A2, which is 0.005 multiplied by 0.010. Okay. So when you solve this, you will get this y dash bar, and this y dash bar comes out to be 0.01592 meter, or you can say that this y bar is equal to 15.92 millimeter. Okay. So what we will do is that we will represent this on element. So I will represent it by using red color. So 15.92 from the top. Neutral axis lies 15.9 millimeter from the top. So mid of 15. So your neutral axis or centroidal axis will be somewhere here. So this distance is y dash bar, and that is equal to 15.92 millimeter. Okay, now you have this. You can see that what is C? C is the maximum distance from neutral axis. It will be either top or bottom. So you can see this is total is 35 from this till this. This is 35, and from this centroidal axis till top it is 15.92. Clear? So C will be equal, maximum distance will be this one. You can see if you subtract 35 millimeter, 35 minus 15.92 will give you 19.08 millimeter. This will be equal to C. Clear? You can see the upper distance from the centroidal axis is 15.92 and lower distance remaining is 19.02, which is C. C is the maximum distance from neutral axis. And for without ribs, also we know that maximum normal stress or bending stress is equal to M into C divided by I. So here we have moment, we have C. What is I? And this I will be no more like we did in rectangular portion without ribs. You can see that this centroidal axis is about centroidal axis, it is not symmetrical. So what we will do, we will apply parallel axis theorem. So I will write by using parallel axis theorem for portion 1. This is 1. This is 1. So we can see that it will be equal to 1 over 12 BH cube. B is 60, so 0.060, and height is 30 millimeter. So we can write in meter is 0.030. Since this centroidal axis or neutral axis away from the center of this rectangular section by this distance, this is D. Clear? So we will write AD square. So area is 0.060 and multiply by 0.030 in D square. What is D? So D is distance from neutral axis till the mid of first section. So this is the distance. And how we can find this? So we know that this distance is 15.92 and this distance is 15. So 15.92 minus 15 will be equal to 0.92 millimeter. Clear? And 0.92 we can also write it y dash is 15.92 millimeter. So in meter it is 0.01592 minus y dash is 15 millimeter. So in meter it is 0.015 meter. So this is D, AD square. So I can write it 1 over 12 BH cube plus AD square. So for 1, 1, 1, 1. That is equal to I1. I plus for 2 portion, it will be equal to 2 times 1 over 12 B2 H2 cube plus A2 into D2 square. Clear? Okay. Now what is, I will write it here, plus 2 times 1 over 12. What is breadth of this web? So breadth is 10 millimeter. You can see 10 millimeter and height is 5. So 1 over 12, 10 millimeter is breadth, which is 0.01. Clear? And height is 5 millimeter. So 0.005 meter whole cube plus area A2, which is 0.01 multiplied by 0.005. Clear? And D square. What about D square? D2. So D2 is distance from this neutral axis till the mid of second section. Clear? So how you can find that? You can find it by using, you can see this distance was this distance. This distance was from the top till the mid of section. This was y2 dash, which is 32.5. Clear? So if you subtract this distance 15.92 from this 32.5, so you will get this distance. distance from this neutral axis till the mid of second section. So 32.5 minus 15.92. So 32.5 is actually 0.0325 meter minus 15.92 is 0.01592 and it is d square. So there will be square. So when you solve this, you will get I will be equal to 0.1642 into 10 raised to power minus 6 meter power 4. Now you have all the values, just plug it in this formula. Sigma max is equal to moment, which is 40 Newton into meter. C is this one, 19.08. So in meter it is equal to 0.01908 meter. Divide by I is 0.1642 into 10 raised to power minus 6 meter power 4. So simplify it, you will get 4.65 into 10 raised to power 6 Newton per square meter, or that will be equal to 4.65 into 10 raised to power 6 Pascal, and in megapascal 4.65 megapascal. So this is the maximum normal stress when we add two small ribs at the bottom of rectangular section. So in this way we have found this is the maximum stress without ribs and this is the maximum stress with ribs. And you can see that if we add ribs, so maximum stress is increasing, but we do not want to increase the stress in the section. So what will be the conclusion? Conclusion is that, let me write it. Conclusion is that this surprising result indicates that the addition of ribs to the cross section will increase the maximum normal stress rather than decrease it. Also, it is increasing the strength, but here the maximum normal stress in the beam is increase. Clear? So, and for this reason, they should be omitted. So preferred design for this beam that resists 40 Newton into meter will be this one. And that was all about this problem 6.14. This was made by on request of one of the subscriber who insisted me to explain this problem. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve example 7.1 that is taken from chapter number 7, Transverse Shear, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the beam shown in figure 7-A is made from two boards. Determine the maximum shear stress in glue necessary to hold the board together along the seam where they are joined. So you can see this is the beam and here there is a roller support and at this end we have pin support, and this beam is acted upon by a uniformly distributed load of 6.5 kilonewton per meter over a length of 4 meter, and this beam is made of two boards that are glued together and the glue is at this point. So you have to determine the maximum shear force in the glue necessary to hold the board together. So let's start with the solution. The first step is that if I remove this roller support at this point, so we will have a reaction force. Let this reaction force is R1, and if you remove this pin support at this point, so you will having reaction force R2. Let this is your point 2 and this is your point 1. So first we will find this R1 and R2 by using equation of equilibrium. So what are these equation of equilibrium? The first equation of equilibrium is that sum of all moments that is acting about point 1 is equal to 0 and taking the counterclockwise moment as positive. So you can see there is a 6.5 kilonewton per meter load, and this load when converted into a point load, so I can say this load will be 6.5 multiplied by 4, clear, and that will be equal to 26 kilonewton. Okay, now this load will act at a distance of 2 meter from either this side or from this side, so whichever you want. So I can write it 2 meter and this will be also 2 meter. So by applying this equation of equilibrium, we can say that this load, which is 26 kilonewton, and the perpendicular distance is now 6 meter, and this is producing clockwise movement, so it will be negative. So I can write it minus 26 multiplied by 6. The second moment about point 1 is this load R2 and perpendicular distance is 8 meter, and this is producing counterclockwise, so it will be positive. So I will write R2 multiplied by 8 is equal to 0. So from here we will get 8 times R2 is equal to 26 multiplied by 6, and this R2 will become equal to 26 multiplied by 6 divided by 8, and when you solve this you will get this R2 will become equal to 19.5 kilonewton. Now we will find this second term, that is R1, by using another equation of equilibrium, that sum of all forces along y direction must be equal to 0. Upward force is taken as positive. So you can see R1 is upward, so plus R1 minus 26 plus R2 is equal to 0. So R1 minus 26 plus 19.5 is kilonewton is equal to 0, and from here we will get R1 will be equal to this, R1 will be equal to 6.5 kilonewton. Now we have this R1 and R2. So what we are going to do is that we will draw the shear force diagram in order to find the maximum shear force, because we know that maximum shearing stress is equal to maximum shear force into Q max divided by I into T. So we will find this maximum shear stress by using the bending moment shear force and shear force diagram. For this I am drawing to this beam, the free bar diagram of this beam. Here we have R1 which is 6.5 kilonewton, and here we have R2 which is 19.5 kilonewton, and there is a distributed load acting over a length of 4 meters. So let this is that distributed load, this length is 4 meter and this length is also 4 meter, and the distributed load was 6.5 kilonewton per meter. 6.5 kilonewton per meter. And when we will use two lines from the end of this beam. So I will draw two lines from the end of beam, and there is a horizontal line to show the length in meter. So this is x in meter, and there we have a shear force in kilonewton. Okay, starting from the very first point, we have R1 which is 6.5. So let me zoom it. Let this division is 5 kilonewton. This is 10. This is 15 kilonewton. So here minus 5, minus 10, minus 15 and minus 20. So I will choose first point. At first point we have R1 and R1 is 6.5. So let 6.5 lies over here. So you can see that moving from point 1 till the point of distributed load, there is no other load, so it will remain horizontal till this point. So I can draw a line like this till this point. Now you can see you have a distributed load over here. So this distributed load when multiplied with this load will give you minus 26. So here you have 6.5 and at this end you have minus 26 and that will go to minus 19.5. So at the end you have minus 19.5, which will be this point, minus 19.5. Now you can see that this distributed load is a horizontal line with 0 degree and it is downward negative. So shear force will be a 1 degree line and its slope will be decreasing. So we can just join these 2 points in order to get this line. And at the end you can see you have plus 19.5. So minus 19.5 plus 19.5 will bring this to 0. So this will be your shear force diagram. Okay, so from this shear force diagram I can write it here. From shear force diagram we see that maximum shear stress absolute value is 19.5 kilonewton. Now you can see that we have find out this Vmax. So we will find this I for this section, which is T section, that is made from the wood. So it is necessary to determine the neutral axis for this beam. So for neutral axis I can first find the centroid or neutral axis of this beam, and this neutral axis lies, for this neutral axis I have formula that y dash is equal to sum of y dash bar into A divided by sum of area. So what I can do is that you can see this is the cross section of the beam. So here I can say we have two things. One is this one, two boards. One is this one and second one is this one. I can write it as number 1. Let this is your first one and this is your second one. And we will take this horizontal line or the base as reference. So from reference line this formula will become equal to y1 bar into a1 plus y2 bar into a2 divided by sum of area a1 plus a2. Now we can see that what is a1. So a1 is equal to this length, width and height is 150. So a1 in meter is 0.03 multiplied by height is 0.150. And what is y1 dash? So y1 dash is distance from this reference line till the mid of this. So let the mid of this is this one. This is y1 dash. And this y1 dash will be equal to 150 divided by 2. This is 150. So 150 divided by 2 is 75 millimeter. So 75 millimeter in meter is 0.075 meter. What is A2? So A2 is this area. You can see. So its area is 150 by 30. So I can write it 150 in meter is 0.150 and 30 is 0.03. And what is y2 dash? So you can see y2 dash is distance from this reference line till the mid of this section. This is your y2. This is reference line. Okay. This is y2 dash. Okay. And this y2 dash is 30 divided by 2. This distance is 15. So I can say total height is 180. So 180 minus 15 is 165. So this y2 is 165 millimeter. And in meter it is 0.165 meter. Now you have a1, y1 dash, a2, y2 dash. Just plug it in this formula. So let me plug it. So you will get y dash bar is equal to y1, which is 0.075, multiplied by area A1 is 0.03, multiplied by 0.150, plus y2 dash is 0.165, multiplied by area is 0.150, multiplied by 0.03, divided by sum of all the areas. So area A1, you can see area A1 and A2 both are same, so I can just write it. I do not have space over here, so I can just simply write it 0.03 multiplied by 0.150. So when you solve this, you will get location of centroidal axis or neutral axis, and that comes out to be 0.012 meter. Or you can say this y dash is equal to 20, 0.12. Okay, make a correction when you calculate it. This y dash is 0.120 meter, or in millimeter it is 120 millimeter. So as I am using meter, so I will use this value, but let me show you that neutral axis from the base will lie, this will be the neutral axis, and this distance will be equal to y dash. This y dash is equal to 120 millimeter. Now what we will do is that we will find moment of inertia I. So for I we have formula by using parallel axis theorem. So for first element, this one, we have 1 over 12 B1 H1 cube plus area A1 into D1 square plus moment of inertia of the second, which is 1 over 2 B2 H2 cube plus area into D2 square. Clear? So how we'll find this? So let's put the value 1 over 12. What is the height of this, base of this? So base is 0.03 meter and height is 0.150 meter. These values are in millimeters, so we will convert this. I can write 1 over 12, base is 0.03 and height is 0.150 cube, plus area. Area is this base, which is 0.03 and height is 0.150. And what is D1? So D1 is distance from neutral axis till the mid of this section. So you can see this distance is 120 and this distance is 75. So you can get 0.120 minus 0.075 will give you D1. So I will write it over here. This distance will be D1. So D1 is 0.120 minus 0.075. Okay, whole square. This will be the moment of inertia of the first, plus 1 over 12. Now you can see that base is, for this is section 2, so base is 0.150 and height will be 0.03. So I can write 0.150 multiply by 0.03 whole cube, plus area will be 0.150 multiplied by 0.03. And what is D2 square? So let me show you over here. D2 is distance from neutral axis till the mid of this section. This is D2. So I can first show you this is D2. And D2 can be obtained if you take this total height, which is 180 millimeter, and then you subtract this 120 and then half of this, which is 15 minus 15, will give you this D2. Clear? So I can write D2 is 0.180 minus okay, D2 is, let me check it again. D2 is distance from neutral axis till the mid of this section. And you can see from the mid of this section, this is y2. So simply we can say 165 minus this distance 120 will give you d2. So I will write it 0.165 minus 0.120 whole square. Okay, when you solve this, you will get the moment of inertia I for this T section wooden beam, and this will be equal to 27 into 10 raised to power minus 6 meter power 4. Now you have the moment of inertia of this beam, clear, and we will find Q max. So Q max can be obtained. We know the formula that Q max will be equal to y dash bar into area, and Q max for this, as we are finding out the maximum shear force for the glue that is in between this 1 and 2. So what we will find the Q max for this region. Okay, so what we will do is that this will be your area where you are finding the Q max at this region. So this will be the area A dash. So I can write this will be area is A, sorry, A, not A dash, A, and this area is 0.150 multiplied by the thickness, which is 0.03. And what will be y dash? So y dash is distance from neutral axis till the mid of this section, and that is d2, and that is 165 minus 120. Clear? Okay, so we can write this that Q max is y dash is 0.165 minus 0.120 into A dash is 0.150 multiplied by 0.03. Now when you solve this Q max by using your calculator, so you will get Q max will be equal to 0.2025 into 10 raised to power minus 3 meter power cubic meter. Clear? And again you can see you have now this value Q max, and what is T? So T is the thickness that will be counted in this portion, because this is the point of joining of these two with one by using glue. So we will take thickness T is 30 millimeter. So I will write it here. T is equal to 30 millimeter, R in meter, it is 0.030 meter. Now you have all the values. What you can do is that you can just plug it, as we are finding maximum shear stress, which is equal to V max into Q max divided by I into T. So V max is this one. You can see that here I have written V max is this one, which is 19.5 kilonewton. So I can write 19.5 into 10 raised to power 3 Newton. What is Q max? So Q max is this one, which is 0.2025 into 10 raised to power minus 3 divided by I, and I, the value of I is there, which is 27 into 10 raised to power minus 6, and thickness is 0.030 meter. So when you solve this, you will get 4.88 megapascal. Now what I can write is that maximum shearing stress at the junction of first board and second board where they have been glued is 4.88 megapascal. Okay, so if I draw the representation of this stress for this beam, so let me draw it over here. Let this is the board, the first board. So the shear stress will be like this. This will be the shear force that will acting like this. Why upward? Because you can see the maximum shear force is 19.5, and that will be at the end, because this will be plus 19.5. So shear force is upward. So if I represent the shear force on this element is like vertical, so this will be V, and the representation of stress will be like this. So this shear stress will be 4.88 megapascal, and that will be tau. Now if I represent it on three-dimensional element, so this representation will be exactly like this, that these shear force are upward, so in order to balance it there will be a longitudinal shear stress. Clear? So this will be the representation, and I will represent it is the glue resistance to the, this is the glue resistance to the longitudinal shear stress that holds the board from slipping at the right hand support. So this was all about this example 7.1. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-75. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Materials by R.C. Hibbeler. So statement is the shaft is supported by smooth thrust bearing at A and smooth general bearing at D. If the shaft has cross section shown, you can see the shaft cross section. The outer radius is 40 millimeter and inner radius is 25 millimeter. Determine the absolute maximum bending stress in the shaft. So this is the shaft. At A we have a smooth general thrust bearing. At D we have smooth general bearing. At B and C we have a 3 kilonewton load that is downward. The length is shown over here. The total length is 3 meter. Clear? So you have to find the absolute maximum bending stress in the shaft. So let's start with the solution. So first step is that if you remove this smooth thrust bearing, so you will be having reaction force exerted by this bearing on the shaft, which is equal to RA. And if you remove this smooth general bearing at D, so it will apply a reaction force RD on the shaft. So we'll find this RA and RD by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0 and taking the counterclockwise movement as positive. So about point A, the first moment will be this 3 kilonewton load and perpendicular distance is 0.75. It is clockwise, so it will be negative. So I will write minus 3 into 0.75. The second moment will be due to this 3 kilonewton load, and now perpendicular distance is this one, which is 0.75 plus 1.5, and that is 2.25, and it is also clockwise, so it will be negative. So I will write minus 3 into 2.25 meter. And the last moment that is produced due to this RD and perpendicular distance is this total is 3, and this is producing clockwise, counterclockwise, so it will be positive, plus RD into 3, and the sum of all this moment about point A must be equal to 0. So when you calculate it, you will get this 3RD will be equal to 9, and from here you will get this RD will be equal to 3 kilonewton. Okay, now you have this RD, so you can find this RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA, which is upward, so RA minus this 3 kilonewton and minus this 3, so minus 3 plus RD, which is plus 3, is equal to 0. So from here this will cancel with this, so RA will also equal to 3 kilonewton. Now we have RA and RB, so we will move toward finding the shear force and bending moment diagram, because we have to find the maximum bending moment and maximum bending stress, and that maximum bending stress is maximum bending moment into C divided by I. So here the hollow circular shaft, so it will be outer radius. So for finding a maximum bending moment, we will draw the shear force and bending moment diagram. So again for that I will take the vertical line from the end of this beam, clear, and then horizontal line to show the length in X in meter. On y-axis we will have shear force that will having unit kilonewton. Let each division is 1.5 kilonewton, so this is 3. Similarly minus 1.5, you can choose as per your required scale or chosen scale. Now you can see that first at RA we have, at point A we have RA, which is 3 kilonewton. So your first point will be this one. Now moving from point A till point B, there is no other shear force, so till this point B this shear force will remain horizontal. Okay, now at this point B we have minus 3, that is downward, so plus 3 minus 3 will bring it to 0. So shear force will change from 3 to 0. Now again from B to C there is no other shear force, so it will remain similar horizontal line till point C. So this is your point C, this is your point B, this is C, so this shear force remain horizontal. Again at point C you have minus 3 downward, so 0 minus 3 will be equal to minus 3, so shear force will change it here and it will be minus 3. And moving from C to D there is no other shear force, so it will remain same horizontal line Clear? And at the end, you can see you have RD, which is plus 3. So minus 3 plus 3 will bring it to 0. Okay. So this is your shear force diagram, SFD, shear force diagram. Now we'll find the bending moment diagram. For that, I will draw a horizontal line again to show the length of beam, and this length will be in meter. And on y-axis, you have moment that will have unit kilonewton into meter. So let one division is 1 kilonewton into meter. This is 2, this is 3. Similarly, minus 1, minus 2. So at x is equal to 0, we have moment is equal to 0. Now the first area under the shear force diagram is this area, and this area is this height, which is 3, and this length is 0.75. So 3 into 0.75 will be equal to 2.25. So at this point, we will have 2.75. So first we'll look at 2.25, sorry. So let this point is 2.25. Now you can see that shear force is a horizontal line with this area is positive and this is 0 degree line. So bending moment will be 1 degree higher. It will be a linear line and slope will be increasing. So you will join these 2 points using straight line. Now here in this region there is shear force is 0, so bending moment will remain constant till this point. So it will be a straight line till this point. This will be 2.25. Now the area under the area under this shear force diagram is minus 3 into 0.75, which is equal to minus 2.25. So plus 2.25 minus 2.25 will bring it to 0 at this point. Clear? So your new point, bending moment at this point will be 0. And you can see that shear force is a horizontal line with this area is negative. So bending moment will be a linear line and slope will be decreasing. So we'll join these 2 points using a straight line, and that will be your BMD, bending moment diagram. Okay. Now from BMD, bending moment diagram, you have bending moment, maximum absolute value of bending moment is equal to 2.25. and unit will be kilonewton into meter. Clear? So this will be the maximum bending moment, will be 2.25 kilonewton into meter. So we have been given the hollow circular shaft, outer and inner radius are given, that is outer is 0.04 and inner is 0.025 meter. So I for circular second moment of inertia of circular shaft is pi by 4 into C outer power 4 minus C inner power 4, where C is the radius. So you can just put the value pi by 4. C outer was 0.04 power 4 minus C inner is 0.025 power 4. Clear? And what about C outer? C outer is the maximum distance from the neutral axis. So you can have all, you have all the values. So you can just put it in this formula that maximum bending stress is equal to maximum bending moment and C outer divided by I. So maximum bending moment is 2.25 kilonewton. So 2.25 into 10 raised to power 3 will be Newton into meter, and C outer is 0.04 divided by I, which is pi by 4 into 0.04 power 4 minus 0.025 power 4. So again, when you calculate it, you will get 52.8 into 10 raised to power 6 Pascal. And when you convert it into megapascal, so maximum bending stress will be equal to 52.8 megapascal, which is the answer of this question. So maximum bending stress for the loading and the hollow circular shaft is calculated is 52.8. That was all about this problem 6-75. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-27. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is draw the shear and moment diagram for the beam. So you can see this is an overhanging beam and there is a triangular load of magnitude W0 at this end. At this end load is 0. There is a roller support at A, and at point B we have pin support. So you have to draw the shear and moment diagram for the beam. So let's start with the solution. So first step is that if you remove this roller support at point A, so you will be having reaction force offered by this support on this beam will be RA, and if you remove this pin support, so there will be a vertical reaction force of RB on this beam by this support. So first we will find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So you can see one load is RA, the second is RB, and the third one is, if this triangular load is converted into a point load, so it will be equal to W1 over 2 into W0 into the length over which act, and this total length of the beam is equal to L. This is L because 2L by 3 plus L by 3 is equal to L, and that will act at a distance of L by 3 from point B or from denser side. So this will be L by 3. Now we apply this equation of equilibrium. So RA into perpendicular distance is 2L by 3 Let me show you. This is RA, and about point B, this perpendicular distance is 2L by 3, and this is producing clockwise, so it will be negative. So I will write minus. The second moment that is produced due to this load and perpendicular distance is L by 3. Clear? And this is producing counterclockwise movement, so it will be positive. Here I have L as well because it is acting over length. So plus 1 over 2, this load, which is 1 over 2 W naught into L, W naught into L, and perpendicular distance is L by 3 is equal to 0. So from here we will get minus 2 RA L divided by 3 plus 1 over 6 W naught L square is equal to 0. So you will get 2 RA L by 3 is equal to 1 over 6 W naught L square, and when you calculate, RA will be equal to W naught L over 4. So this is the value of RA. Now we'll find this RB by using equation of equilibrium, that sum of all force along y direction must be equal to 0 and upward force is taken as positive. So RA and RB are upward, so RA is W naught L by 4 minus this force, which is W naught 1 over 2 W naught into L plus RB is equal to 0. So if you take LCM, so this will be 4, so it will be W naught L minus 2 W naught into L plus RB is equal to 0. So this will give you 4 minus W naught into L plus RB. So from here you will get this RB will be equal to W naught L over 4. Now you have RA and RB. So what we are going to do is that we will cut the beam at this and at this section. That this is section AA and this is section BB, and we will find the equation of shear and moment as a function of X. Clear? And then we will put the value of X to find the shear and moment, and then draw the shear force and bending moment diagram. So first step is that if you cut this beam over here, clear, and let this distance is X, this is section 1, and draw the free body diagram. So let me draw it first. This is the beam, clear, and you will be having a triangular load. Clear? This is the triangular load. This is the distance X where you cut this beam, and when you cut it, you will be having a shear force V, and you will be having moment M. This is your point 1. Clear? Now you can see that here the load is W naught. So if you take the ratio, we have two similar triangular. One is this one, and the other one is this one. So this is for the length of L, and this is for length of X. Clear? So by using similar triangles, if I take the ratio, this W naught over length L, W naught over length L will be equal to, here let the magnitude is W. So W divided by this distance X. So W divided by X. So where we will find W will be equal to W naught into X divided by L. So here the magnitude will be W is equal to W naught into X by L. Now when you convert this triangular load into point load or concentrated load, so it will be equal to 1 over 2 this load, which is W naught X over L, and the length over which act, and that length is X, and that will be acting at a distance of X by 3 from this point 1. Now we'll find this V and moment by using equation of equilibrium. So first equation of equilibrium is that sum of all force along y direction must be equal to 0 and upward force is taken as positive. And remember that section AA is for X is greater or equal to 0 and less or equal to L by 3. So X start from here is equal to 0, and at here you can see X is L by 3. So this equation will be valid for this region. Clear? Now V is downward, so minus V minus this load is downward. So minus 1 over 2 W naught X square over L is equal to 0. So from here you will get V is equal to minus W naught X square over 2L. This is your equation number 1. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about point 1, the one moment is due to this, which is this load into perpendicular distance is X by 3, and this is producing counterclockwise movement, so it will be positive. And this external moment which we have taken as this will be positive. Now you can see that this load is producing counterclockwise movement, so in order to balance it, it will be in this direction. So let me correct it. This direction is this. So this minus moment, which is clockwise, plus 1 over 2 into W naught X square over L into perpendicular distance is X by 3 is equal to 0. So from here you will get this moment will be equal to W naught X cube over 6L. Clear? And this will be your equation number 2. So this equation 1 and, let me write it, equation 1 and 2 are valid for X is greater than or equal to 0 and less than L by 3. Now what we will do is that we will cut the beam at any region, that this is section 2, and this region is X is greater than or X is greater than L by 3 and less or equal to L. Clear? And we will draw the free body diagram. So let me draw it over here. So this is the beam. Clear? There is a triangular load over here. Clear? This is the triangular load. At distance of L by 3, we have RA. So this is L by 3. And this is RA. And RA is W naught L over 4. And the total distance from this till the end of the beam is X, where we have cut this beam. So the remaining will be equal to X minus L by 3. And what about the magnitude over here? It will be the same, just like W naught X over L, because you can see you will have a two triangle, similar triangle. One is this one and the second one is this one. So W naught over L is equal to W over X, and this W will be equal to W naught X over L. Okay, W naught. So when you cut it, you will be having a shear force, clear, like this, and you will be having a moment that will be counterclockwise. Why? Because you can see now you have this force and this force as well. So we have taken it counterclockwise because its effect will give you a positive moment. Okay, so this is your point 2, because it is section at point 2. So when you convert this triangular load into a point load, so it will be equal to 1 over 2 this load, which is W naught X over L, clear, and it will act at a distance of X by 3, because X is the total length. It will be X by 3. Now we'll find this by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. And remember that this is for section 2-2, and here X is greater than L by 3 and less or equal to L. Clear? So W naught L by 4, which is acting upward, clear, minus this load which is downward, minus W naught X over L. Clear? So this load here, you can see 1 over 2, this load into the length over which that is X. So it will be W naught X square minus W naught X square over L. Clear? And the last thing is that minus V is equal to 0. So from here, this V will be equal to minus, it will be equal to W naught L by 4 minus W naught X square over L. Or you can say this V is equal to minus W naught X square over 2L. Here you can see you have 2 as well, so it will be minus 2. Clear? So minus W naught X square over 2L plus W naught L by 4. This is your equation number 3. Now you'll find movement by using equation of equilibrium, that sum of all movement about point T is equal to 0 and taking the counterclockwise movement as positive. So about point 2, first movement is due to this W naught L by 4, and perpendicular distance is X minus L by 3. This is producing clockwise movement, so it will be negative. So I will write minus W naught L by 4 into perpendicular distance is X minus L by 3. The second movement will be due to this load, and perpendicular distance is X by 3, and it is producing counterclockwise, so it will be positive. So I will write this load, which is plus 1 W naught X square over L into perpendicular distance is X by 3, and there is external movement which is positive. Their sum must be equal to 0. So when you solve this, you will get this movement will be equal to minus W naught L over 4 into X minus L by 3 plus W naught X cube over 3L. Okay, just wait a minute. This is W naught X square over W naught X square over 2L. So this will become equal to 6L. Okay, now it's okay. This is your, this will be positive, M will be equal to, this will be positive, and this will become negative. Okay, so this is your equation number 4. Now we have equation 1, 2, 3, 4. This equation 3 and 4 are valid for X is greater than L by 3 and less or equal to L. Clear? Now we'll move to draw the shear force and bending moment diagram. For that, I have to copy these equations. Let me copy these equations, some portions, so that we can move toward next page. I will copy it. I will move to second page and will paste here. Okay. So for shear force and bending moment diagram, I have to draw vertical lines from the end of this beam. You can see here, and there is a horizontal line to show the length in X, which is not known either in meter or in inches. So here we will draw the V. Now first, what we will do is that you have all these equations. So for X is equal to 0, put in equation number 1. Equation 1 is this one. So if you put X is equal to 0, so you will have V is equal to 0. Now for X is equal to L by 3, put in put in equation number 1. So what we will get if you put x replaced with L by 3, so you will get shear force will be equal to minus 1 over 8 W naught into L. You can put it and you will get this value. So this, can we correct it? This is V is minus 1 over 18 W naught into L. We can put it V is equal to minus W naught. You will replace L by 3 whole square over 2L. So that will be minus W naught L square over 18 L, which is equal to minus W naught L over 18. Clear? So I will again remove this. Now for x is equal to L. Clear? So put the value, put in equation number 3. So this is your equation number 3. So when you put x is equal to 3 in that, so what you will get is that you will get V is equal to minus W naught L over 4. Now you can see that at the end you will have RB, which is equal to W naught L over 4. It means that this will bring it to 0. So in between, let me plot it as well. So at x is equal to 0, we have first point is this one. At x is equal to L by 3, which is this one. Clear? So we have V is equal to minus 18. So let minus 18 W naught L minus W naught L over 18. Minus W naught L over 18 is this one. Clear? And you can see you have RA as well over here. So which is W naught L over 4. So minus W naught L over 18 plus W naught L over 4 will bring it to 7 W naught L over 36. Okay. So you can see that this the shear force, the loading is triangular. So the shear force will be second degree curve and it will be like this. So let me join first these 2 points like this, like a curve. At this point you have plus 40, which will cause it to 7. So let 7 W naught L over 36 is this point. So shear force will change from this till this point. This is the point. Okay. Now at the end we have minus W naught L over 4, which let this is minus W naught L over 4. And at the end you have plus, which will cause it to come to 0. And you can see that this load is again a linear load. So shear force will be a second degree curve and it will be like this. It will be like this. So we'll join these 2 points by using curve, not a straight line. I'm trying it to draw like a curve. Okay. Now here you can see the shear force is equal to 0. Clear? And we will find the location where this shear force acts, because at this location the bending moment will be the maximum. So you will find this value of x, which is not known. So what we will do is that put V is equal to 0 in equation number 3. So it will be equal to 0 will be equal to minus W naught x square over 2L plus W naught L over 4. So what we will get from here, that x will be equal to, let me check it. This will give you x square is equal to L square over 2 and x will be equal to 0.707 L. Clear? So this is x is equal to 0.707 L. So you can put this value of x in this equation number 3. So you will get V will be equal to 0. We will move toward bending moment diagram. So for bending moment diagram, I will again draw a horizontal line, and here x will be the length and on y-axis we have moment. So what we will do is that for x is equal to 0, put in equation number 2. This is equation number 2. So if you put x is equal to 0, so moment will be equal to 0. So your first point will be this one. Here moment is 0. Okay. So for x is equal to L by 3, put in equation number 2. Equation number 2. So this is your equation number 2. You can see. So if you put x is equal to L by 3, so what we will get after the calculation, or after simplifying, you will get moment will be equal to 0.00617 W naught L square. I have already done it, but for reducing the length of the video, you can do it by yourself and you will get this value. Now you can see this is a positive value. Clear? This is a positive value. So while representing this positive value on moment diagram, it will cause the bending moment to go downward. So let this point is minus 0.00617 WL square. This is a convention given in the book. And you can see that this shear force is a second degree curve, and you can see the moment is 3 degree equation. So it will be just like, it will be also a third degree curve, and the bending moment will be like this, starting from 0 till this end. Okay. Now for x is equal to 0.707 L, put it in equation number 4. That will give you maximum bending moment. This is your equation number 4. So if you replace x with 0.707 L, so you will get the maximum moment, which will be equal to, 0.0345 W naught L square. So we locate this point, clear, and this will give you the point will be like. Welcome back. In this video, we are going to solve problem 6-193 that is taken from chapter number 6 bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is draw the shear and movement diagram for the shaft if it is subjected to vertical loadings of belt, gear and flywheel. The bearing at A and B exert only vertical reaction on the shaft. So you can see this is the shaft and this is bearing A and B that exert only vertical reaction. Clear? This is the gear where there is a 450 Newton load. There is a flywheel or belt. You can see this 300 Newton and there is a flywheel which have 150 Newton. So you have to draw the shear and movement diagram for the shaft. So let's start with the solution. So first step is that if you remove this bearing at A, so you'll be having a reaction force. Let this is RA, and if you remove this bearing at point B, so you will be having a reaction force which will be equal to RB. This distance is 200 millimeter or 0.2 meter. This is 400 millimeter or 0.4 meter. This is 300 millimeter or 0.3. So we'll find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, the first moment will be 450 into perpendicular distance is 0.2, and this is producing clockwise, so it will be negative. So I will write it minus 450 into perpendicular distance is 0.2 meter. The second moment about point A is this 300 Newton load and the perpendicular distance is 0.6 meter. And this is producing counterclockwise movement, so it will be positive. So plus 300 multiplied by 0.6 meter. The third moment will be due to this RB into perpendicular distance is now 0.9 meter. You can add them. This is 0.9. This is counterclockwise, so it will be positive. So I will write plus RB into 0.9 meter. And the last moment that is due to this 150 Newton load and now perpendicular distance is 1.1 meter, because when you add it, it will be 1.1 meter. Okay, so we will write this is producing clockwise movement, so it will be negative. So I will write minus 150 into 1.1 meter, and this will be equal to 0. So when you solve this from here, you will get this RB will be equal to 83.33 Newton. Now we will find this RA by using equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA is upward, so RA, this 450 is downward, minus 450 plus this force is upward, so it will be positive, plus RB which is 83.33 Newton, and minus 150 is equal to 0. So when you solve this, you will get RA will be equal to 217 Newton. Now you have RA and RB, so we will draw the shear force and bending moment diagram. So what we will do is that we will take two lines from the end of this beam. One is this one and other one is this one. There is a horizontal line to show the length that will be in meter, x in meter. On y-axis, you will be having a shear force having unit Newton. Okay, so we'll take one division is equal to 50. So this is 50, this is 100, this is 150, this is 200. Similarly, minus 50, it will be minus 50, minus 100, minus 150, minus 200, and minus 250. So we'll first draw the shear force diagram. Now at this point, you can see you have RA, which is 217. So we'll locate 217. This point is 217 Newton. So moving from point A till this load, there is no other shear force, so it will remain horizontal till this point. Okay. Now here we have minus 450 Newton that is acting downwards. So 217 minus 450 will cause it minus 233 Newton. So at this point, the load will be minus 233. So let 233 is this point minus 233. So your shear force will change from 217 to minus 233. And moving from this load till this mid, there is no other shear force, so it will remain same horizontal till this point. Clear? And we will draw a horizontal line. Okay. Now at this point, you can see you have plus 300 upward. So minus 233 plus 300 will cause it to move to 66.7 Newton. So the load will be 66.7. So let 66.7 is this load, this point, 66.7. You can choose your own scale as well. Okay, this is 67. Now moving from this mid till point B, there is no other shear force, so it will remain same horizontal till this point. So we will draw a horizontal line till this point. And again, you can see you have plus RB. So 66.7 plus RB is 83.33 will be equal to 150 Newton. So shear force will change to 150. So this will move to this point. This point is 150 Newton. And moving from 150 till end, there is no other shear force, so it will remain horizontal. And at the end, you can see 150, that is downward. So plus 150 minus 150 will bring it to 0. So this is your shear force diagram. Now we'll draw the bending moment diagram. So for that, again, I will need the space. So this is your horizontal line to show x in meter, and here you have moment. Let each division is 25. So this is 50. Similarly, minus 25 and minus 50. Okay. At point x is equal to 0, we have moment is equal to 0. So your first point will be this one. Now, first area under the shear force diagram is this area. And you can see this area is, this height is 217 and this width is 0.2. So 217 multiplied by 0.2 is equal to 43.3 Newton into meter. So we'll look at 43.3. So let this is 43.3. This point is 43.3 Newton into meter. The unit is Newton into meter. And you can see shear force is a horizontal line with 0 degrees. So bending moment will be 1 degree higher and slope will be increasing. So we'll join these 2 points using straight line. Now the second area under the shear force diagram is this area, and this area is equal to minus 233 multiplied by this 0.4, and this will be equal to minus 93.3. So plus 43.3 minus 93.3 will cause it to minus 50 at this length. So we'll plot minus 50 at this length. So minus 50 is this point. Okay. Now this shear force is a horizontal line with 0 degree and this area is negative. So bending moment will be 1 degree higher and slope will be decreasing. So we'll join these 2 points using a straight line. This is minus 50. Now moving further, the third area under the shear force diagram is this area, and this area is, you can see height is 66.7 and this width is 0.3, and that will give you 20.01. So minus 50 plus 20.01 will cause it to minus 30. So at this length we will be having minus 30. So we'll plot minus 30. So let minus 30 is this point. This is minus 30. And you can see this shear force is a horizontal line with a positive area. So bending moment will be 1 degree higher and slope will be increasing. So we'll join these 2 points using a straight line. The last area under the shear force diagram is this area, and this area is 150 multiplied by this 0.2, which is equal to plus 30. So minus 30 plus 30 will be equal to 0 at this point, and we will get the bending moment like this. We will get a straight line and the slope will be increasing because the shear force area under the shear force is positive area, and this is a 0 degree line. So this is your bending moment diagram. And that was all about this problem 6-193. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-157. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. And the topic which we are covering is stress concentration. So statement is the step bar has a thickness of 15 millimeter. Determine the maximum moment that can be applied to its end if it is made up of material having allowable bending stress of 200 megapascal. So you can see this is the step rod. So here the thickness is 45, here thickness is 30, and here thickness is 10. And we have a fillet of 3 millimeter over here, fillet of 6 millimeter over here. So this is a step rod, and the moment M is applied on its end. So you have to find the maximum moment that can be applied. So let's start with the solution. So what we will get, you can see that we have 2 fillets over here. So there will be 2 stress concentration factors. So I will find them first. So stress concentration factor K for both these 2 fillets. So now for smaller section, let me show you the smaller section. For smaller section, you can see that this is the smaller section. Clear? So we'll find K for this smaller section. Clear? For that we will need W by H and R by H in order to calculate K. So here you can see that this is W. Clear? So W by H, W by H. So W here is 30 and H here is 10. So W by 10 will be it will give you 3. And what about by R by H? So you can see here fillet is 6 millimeter. So 6 divided by H is 10. So 6 by 10, and that will give you 0.6. So what we will do is that we will find this K, which is stress concentration factor. So you can see here this is 0.6. So you will take this vertical line, clear? And W by H is 3. So you can see this is the graph. So it is coinciding over here, clear? So if you move toward horizontal, so this K will be equal to 1.2. So I will write it here. K is equal to 1.2. Now we will find for larger section. Let me choose another color. For larger section, what will be W by H and R by H. So you can see here for larger section, this will be W, and that is 45. So I will write 45, and this will be your smaller section in 30. So 45 divided by 30 will give you 1.5. Similarly, R by H, here R is 3 millimeters, so 3 divided by H is 30, and that will give you 0.1. Now we will find this K value by using this table. So you can see this is 0.1. So if I draw a vertical line over here, so this is 0.1 and 1.5. So this is, you can see this is W1.5, this graph. So if I proceed it, so this will be the point. And here you can see that if I remove this line, so you can see this graph will meet it at this point. So this will be your K, and that is 1.77. So I will write K value for this larger section, and that is 1.77. Now we will find allowable bending stress. We have been given allowable bending stress. So from here, we will calculate the moment. So we know that allowable bending stress is equal to K times M into C divided by I. Clear? So for smaller section, if you cut it, so you can see, you will draw the cross-sectional view will be like this. So this thickness is given as 15 millimeter, and this height is 10 millimeter. So thickness is 15 millimeter and height is 10 millimeter. This is 10 millimeter. So if you divide it in half, so this will be its neutral axis, and C is the distance from neutral axis till top or bottom. So this is C, and C will be equal to 10 divided by 2, which is equal to 5 millimeter. So C is 5 millimeter, which in meter is 0.005 meter. And what about I? So moment of inertia for this rectangular cross section will be 1 over 12 BH cube. So 1 over 12, B is 15 millimeter, which is 0.1015, and H is 10 millimeter, which is 0.00, which is 0.01 cube. And this is also, this will give you I. Now we have allowable bending stress, we have K, we have C, and we have M. So from here you can see that M will be equal to sigma allowable into I divided by K into C. So put the value. Allowable bending stress is 200 megapascal. So I will write 200 megapascal, 200 into 10 to the power 6 multiplied by I, which is 1 over 12, 0.015, and H cube is 0.01 cube, divided by K. K for smaller section is 1.2. So 1.2 times C, and C is 0.005. When you calculate it, you will get moment will be equal to 41.7 Newton into meter. The unit will be Newton into meter. And this moment is for smaller section. Now we will move toward larger section. So for larger section, again, the moment equation is same, which is equal to sigma allowable into I divided by K into C. So you can see here that for larger section, it will be like this, the cross section. Since thickness remains same, which is 15 millimeter, but here you can see the height will be equal to 30 millimeter. Clear? So I will draw the cross section 30. This height is 30 millimeter, and this width is 15 millimeter. 15 millimeter. So if you take the half of this, this will be its neutral axis, and C will be this distance. This will be your C, and C will be equal to 30 divided by 2, which is equal to 15 millimeter, and C in meter is 0.015 meter. What about I? I is the moment of inertia. So for that, it will be equal to 1 over 12. Its breadth, which is 15 millimeter, and in meter it is 0.015, and height is 30 millimeter. So 30 is 0.030 cube. Clear? And K we have calculated for larger section is 1.77. Now you have all the values. Sigma allowable is 200 megapascal. So 200 into 10 to the power 6 multiplied by I is 1 over 12 to 0.015 multiplied by 0.01 cube divided by K, which is 1.77 multiplied by C. C is here is 0.0. C is 0.015. Now when you calculate all these values on right side, you will get moment will be equal to 254 Newton into meter. And this moment is for larger section. Now we have two moment. One is this one, and the second one is this one. So one is less than second moment. So largest moment that can be applied and will be safe is M is equal to 41.7 Newton. So this is the moment that we can apply on this system, so it will be safe. Now, most of the student ask, since this value is the largest, so why we select this value? So answer is that if you take this moment, clear, and put in this formula. Let me show. If you take this moment and put it in this formula, so you will get allowable bending stress. You will get the stress, clear, which is less than allowable. So, and again, if you put this value for the largest section in this, so your stress will be less than the allowable for larger section. So it will be safe. What if we use this value in this equation? So your stress will greater than allowable, so it will fail. Hence, we select this smallest value, and that is the largest moment that can be applied on this system. And this was all about this problem 6-157. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-64. This problem is taken from chapter number 1, Stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is a vertical force of P 1500 is applied to the bell crank. Determine the average normal stress developed in 10 mm diameter of rod CD and average shear stress developed in 6 mm diameter pin B that is subjected to double shear. So you can see this is the bell crank which is applied a load of 1500 Newton, and this is the rod CD which is used to support this bell crank. And there is a pin support at point B. So this pin having diameter of 6 mm, while this rod CD has diameter of 10 mm. So you have to find the average normal stress in this CD, and there is a pin. You have to find the shearing stress in that pin. So let's start with the solution. So if you take the bell crank free body diagram FBD. So what if we remove this pin support at point B? So you will be having a vertical reaction force which is represented as By, and there will be a horizontal reaction force which is represented as Bx. Always try to draw it separately for saving time. I'm drawing it over here. And the rod CD exert a force FCD in this direction. You can see that this force is downward, causing the rod, causing it to move itward. As a result, the rod exert force in this direction, which is FCD. So we'll find this FCD, Bx, and By using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So about point B, first moment will be P into perpendicular distance is 450, and this is producing clockwise, so it will be negative. We will convert this 450 millimeter into meter, which is 0.45 meter. So P into 0.45. And I will also put the value of P, which is given as 1500. So 1500 into 0.45. And you can see that this FC is producing counterclockwise movement, because perpendicular distance is this one. And this is the force. About point B, it is producing counterclockwise movement, so it will be positive. So how we will get this vertical distance? So you can see if I draw perpendicular line, so this is 45. So this will be also 45. And this distance will be equal to, if you take sine of 45 degree, okay, let me explain it over here. You can see you have one, this FCD is 300 millimeters. So you can see you have one portion is this one, another one is this one. This is the perpendicular distance. So if you take sine of 45 degree, so it will be equal to, let this is y. It will be y divided by CB, which is 300 millimeter. So 300 millimeter. So y will be equal to, this is in millimeter. So y will be equal to 300 into sine of 45 degree, and the unit will be millimeter. So if you want to convert it into meter, it will be 0.30 sine of 45 degree. Now you can see this FCD and perpendicular distance is this one. Clear? This is the perpendicular distance, and it is producing counterclockwise movement, so it will be positive. So I can write plus FCD into 0.30 sine of 45 degree, and it will convert, the unit will be in meter. Okay, now their sum must be equal to 0. So from here you will get FCD is equal to 1500 multiplied by 0.45 divided by 0.30 sine of 45 degree, and that will give you 3181.98 Newton. Now we'll find Bx and By using another equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. Now you can see that we have one force Bx is in this direction, which is positive, and FCD is in opposite direction. Their sum must be equal to 0. So I can write Bx minus FCD is equal to 0. So Bx should be equal to FCD for equilibrium, and FCD is 3181.98 Newton. The last thing is that we can find the third force, which is vertical By, and it can be found by using this equation of equilibrium. So By minus this P, which is 1500, is equal to 0. So from here you will get By is equal to 1500 Newton. Now you have all three forces. So what we will go is that force in this rod is this one, FCD 3181. Clear? So what we are going to find the average normal stress in rod CD, which is equal to force in rod CD divided by area of CD. So force in rod CD is 3181.98. Diameter of rod CD is given as 10 millimeter, which is equal to 0.01 millimeter. Clear? So we will use this, and diameter of it is equal to pi by 4 d square, and d is 0.01 square. So it is 3181.98, and diameter will comes out to be 78.54 into 10 to the power minus 6. Okay. Now if you further simply calculate it, so you will get average normal stress in rod CD comes out to be 40.5 into 10 to the power 6 Pascal, and you will get average normal stress in rod CD will be equal to 40.5 megapascal, which is the answer of our first part. Now we'll move towards second part, and in second part we have been asked to find the average shear stress in pin B. Okay, you can see here that this is By and this is By and this is Bx. So if you draw it by using head to tail rule, clear? So there will be a resultant force which will be B, and that will act on this pin B. Clear? So how we can find this? Because you can see one is vertical component By. Let me draw it. This is the B, this is By, and this is Bx. Clear? So by using Pythagoras theorem, B will be equal to Bx square plus By square under the root. So we will calculate this B by using Pythagoras theorem. So B is equal to Bx square plus By square under the root. Put the value Bx is 3181.98 square plus By is 1500 square under the root. So you will get this B will be equal to 3517.81 Newton. Now you have this B. So you can see if I draw this pin like this, if I want to draw the pin like this at B, so this B is acting over here. And it is given that it is double shear because there are two supports, so VB and VB. So this shear force will be equal to, this B will be equal to 2V, double shear. So shear force will be equal to B by 2. And 3517.81 divided by 2 will give you the shear force VB on the pin. And this shear force comes out to be 1758.91 Newton. Now you have shear force. We know that average shearing stress is equal to shear force divided by shear area, which is area of this pin B. So put the value 1758.91. The diameter of this pin is given as 6 millimeter, which is equal to 0.006 meter. So what will be the diameter? So diameter is pi by 4 d square. D is 0.006 square. And when you calculate it, it will give you 62.2 into 10 to the power 6 Pascal. And in term of megapascal, it will be 62.2 megapascal. And that is the answer of our second part. And this was all about this problem 1-64. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. I will suggest you to try this problem by your own, and if you feel any difficulty, you can ask. Thank you. Welcome back. Problem 1-81. This problem is taken from chapter number 1, that is stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the steel pipe is supported on circular base plate and concrete pedestal. If normal failure stress for the steel is 350 megapascal, determine the minimum thickness T of the pipe if it support the force of 500 kilonewton. Use a factor of safety against the failure is 1.5. Also find the minimum radius R of this base plate so that minimum factor of safety against the failure of concrete due to bearing is 2.5. The failure bearing stress for concrete is 25 megapascal. So you can see this is the pipe having axial load of 500 kilonewton. The outer radius is 100 millimeter and inner radius is not known, and thickness T is also not known. And this is the base plate that is mounted on this concrete base. Clear? So we have been given all the data. So you have to find this thickness T and minimum radius R of this base plate. So let's start with the solution. We can see we have steel plate and concrete. So we know that allowable normal stress for steel is equal to this load, which is acting as 500 P divided by the area of this pipe. Okay, clear? Area of steel pipe. And similarly, allowable stress, bearing stress for concrete is equal to this load P divided by the area of this concrete. So area of this concrete is similar to this area of this base plate. So area of concrete, you can see. Okay, now what we will do is that we will find this as area of steel, this is equal to P, and area of this pipe, hollow pipe, will be equal to pi by 4 or pi r outer square minus r inner square. Clear? And similarly here, this will give you allowable stress in steel, and allowable stress in concrete is equal to P divided by area of concrete. So which will be the same for this base plate, so it will be pi r square. Clear? So it will be pi r square. Now we will calculate this allowable stress in steel and allowable stress in concrete. So we know that for steel, first I will calculate for steel. So for steel, we know that factor of safety is equal to failure stress, clear, allowable stress in failure divided by allowable stress working, allowable, what I have written, let me correct it. Failure stress in steel is equal to allowable stress in steel. So factor of safety for steel is given as 1.5. We are finding allowable stress. So allowable stress in steel, which is allowed and will be safe, will be equal to failure stress in steel divided by factor of safety. And that will be equal to 350 megapascal divided by 1.5. And this will give you 233.3 megapascal in steel. Clear? So I will write it. We get allowable normal stress in steel is equal to 233.3 megapascal. Now for concrete, we have also the same formula, which is that factor of safety is equal to failure stress in concrete divided by allowable stress in concrete. So from here you will get allowable stress in concrete is equal to failure stress in concrete divided by factor of safety. So put the value, allowable stress is 25 in concrete and factor of safety is 2.45. So I will write 25 divided by 2.5 will give you 10 megapascal. Clear? Concrete. Now what we will do is that we have this value, we have this value, we have R naught. So we will calculate for steel. So let me choose another color. For steel, we know that allowable normal stress for steel is equal to P divided by pi into R naught square minus R I square. So this is Ri square. This is 233.3. Allowable normal stress is 233.3 megapascal. So 10 to the power 6 is equal to P is given as 500 kilonewton. So I will write 500 into 10 to the power 3 divided by pi and R naught, which is 100 millimeter. So R naught is 100 millimeter and in meter it is 0.1 meter. And Ri is not known. So this is Ri. Clear? So 0.1 square minus Ri square. So from here you will get pi into 0.1 square minus Ri square is equal to 500 multiplied by 10 raised to the power 3 divided by 233.3 into 10 raised to the power 6. And we will get pi into 0.1 square minus pi into Ri square is equal to 500 into 10 raised to the power 3 divided by 233.3 into 10 raised to the power 6. So what we will get is that pi into 0.1 square minus this value 500 into 10 raised to the power 3 divided by 233.3 into 10 raised to the power 6 will be equal to pi Ri square. And if you divide Ri on pi on both sides, clear? So you will get 0.1 square minus 500 into 10 raised to the power 3 divided by pi into 233.3 into 10 raised to the power 6 will be equal to Ri square. And if you take under root on both sides, so Ri will be equal to 0.09653 meter. So in term of meter, it will be equal to millimeter, it will be 96.53 millimeter. Now you have Ri. So we know that Ri plus T is equal to R outer. Let me show you here. You can see Ri. This is Ri and this is T will equal to R naught. So you can put Ri is 96.53 plus thickness is not known and R naught is 100 millimeter. So thickness will be equal to 100 minus 96.53 millimeter. So from here you will get the thickness of this steel pipe is 3.47 millimeter. So this is the answer of our first part. Now we'll move towards second part, and in second part we have been find the radius of this base plate. Clear? So we know that we use this formula, and allowable concrete is 10 megapascal. So we know that allowable stress in concrete is equal to P divided by pi R square. So from here, this R square will be equal to P divided by pi into allowable stress for concrete. So put the value P is 500 kilonewton, so 500 into 10 raised to power 3 divided by pi, and allowable stress is 10 megapascal, so 10 into 10 raised to power 6 will be equal to R square. And when you take under root on both sides, square root on both sides, so you will get this as R will be equal to 0.1262 meter, or this R will be equal to, in millimeter it will be 126 millimeter. And that is the answer of our second part. So that was all about this problem 1-81. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. And I will request you to share these videos with your friends and help me in growing further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-64. This problem is taken from chapter number 1, stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is a vertical force of P 1500 is applied to the bell crank. Determine the average normal stress developed in 10 mm diameter of rod CD and average shear stress developed in 6 mm diameter pin B that is subjected to double shear. So you can see this is the bell crank which is applied a load of 1500 Newton, and this is the rod CD which is used to support this bell crank. And there is a pin support at point B. So this pin having diameter of 6 mm, while this rod CD has diameter of 10 mm. So you have to find the average normal stress in this CD, and there is a pin. You have to find the shearing stress in that pin. So let's start with the solution. So if you take the bell crank free body diagram FBD. So what if we remove this pin support at point B? So you will be having a vertical reaction force which is represented as By, and there will be a horizontal reaction force which is represented as Bx. Always try to draw it separately for saving time and drawing it over here. And the rod CD exert a force FCD in this direction. You can see that this force is downward, causing the rod causing it to move itward. As a result, the rod exert force in this direction, which is FCD. So we'll find this FCD, Bx, and By using equation of equilibrium. So first equation of equilibrium is that sum of all movements about point B is equal to 0, and taking the counterclockwise movement as positive. So about point B, first movement will be P into perpendicular distance is 450, and this is producing clockwise, so it will be negative. We will convert this 450 millimeter into meter, which is 0.45 meter. So P into 0.45, and I will also put the value of P which is given as 1500. So 1500 into 0.45, and you can see that this FC is producing counterclockwise movement because perpendicular distance is this one, and this is the force. About point B it is producing counterclockwise movement, so it will be positive. So how we will get this vertical distance? So you can see if I draw perpendicular line, so this is 45, so this will be also 45, and this distance will be equal to, if you take sine of 45 degree. Okay, let me explain it over here. You can see you have one, this FCD is 300 millimeters. So you can see you have one portion is this one, another one is this one. This is the perpendicular distance. So if you take sine of 45 degree, so it will be equal to, let this is y, it will be y divided by CB, which is 300 millimeter. So 300 millimeter, so y will be equal to, this is in millimeter, so y will be equal to 300 into sine of 45 degree, and the unit will be millimeter. So if you want to convert it into meter, it will be 0.30 sine of 45 degree. Now you can see this FCD and perpendicular distance is this one here. This is the perpendicular distance, and it is producing counterclockwise movement, so it will be positive. So I can write plus FCD into 0.30 sine of 45 degree, and it will convert, the unit will be in meter. Okay, now their sum must be equal to 0. So from here you will get FCD is equal to 1500 multiplied by 0.45 divided by 0.30 sine of 45 degree, and that will give you 3181.98 Newton. Now we'll find Bx and By using another equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. Now you can see that we have one force Bx is in this direction, which is positive, and FCD is in opposite direction. Their sum must be equal to 0. So I can write Bx minus FCD is equal to 0. So Bx should be equal to FCD for equilibrium, and FCD is 3181.98 Newton. The last thing is that we can find the third force, which is vertical By, and it can be found by using this equation of equilibrium. So By minus this P, which is 1500, is equal to 0. So from here you will get By is equal to 1500 Newton. Now you have all three forces. So what we will go is that force in this rod is this one, FCD 3181. Yeah. So what we are going to find the average normal stress in rod CD, which is equal to force in rod CD divided by area of CD. So force in rod CD is 3181.98. Diameter of rod CD is given as 10 millimeter, which is equal to 0.01 meter. Yeah. So we will use this, and diameter of it is equal to pi by 4 d square, and d is 0.01 square. So it is 3181.98, and diameter will comes out to be 78.54 into 10 to the power minus 6. Okay. Now if you further simply calculate it, so you will get average normal stress in rod CD comes out to be 40.5 into 10 to the power 6 Pascal, and you will get average normal stress in rod CD will be equal to 40.5 megapascal, which is the answer of our first part. Now we'll move towards second part, and in second part we have been asked to find the average shear stress in pin B. Okay. You can see here that this is By, and this is By, and this is Bx. So if you draw it by using head to tail rule. Clear? So there will be a resultant force which will be B, and that will act on this pin B. Clear? So how we can find this? Because you can see one is vertical component By. Let me draw it. This is the B, this is By, and this is Bx. Clear? So by using Pythagoras theorem, B will be equal to Bx square plus By square under the root. So we will calculate this B by using Pythagoras theorem. So B is equal to Bx square plus By square under the root. Put the value Bx is 3181.98 square plus By is 1500 square under the root. So you will get this B will be equal to 3517.81 Newton. Now you have this B. So you can see if I draw this pin like this, if I want to draw the pin like this at B, so this B is acting over here. And it is given that it is double shear because there are two supports, so VB and VB. So this shear force will be equal to, this B will be equal to 2V, double shear. So shear force will be equal to B by 2. And 3517.81 divided by 2 will give you the shear force VB on the pin. And this shear force comes out to be 1758.91 Newton. Now you have shear force. We know that every shearing stress is equal to shear force divided by shear area, which is area of this pin B. So put the value 1758.91. The diameter of this pin is given as 6 millimeter, which is equal to 0.006 meter. So what will be the diameter? So diameter is pi by 4 d square. D is 0.006 square. And when you calculate it, it will give you 62.2 into 10 to the power 6 Pascal. And in terms of megapascal, it will be 62.2 megapascal. And that is the answer of our second part. And this was all about this problem 1-64. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. I will suggest you to try this problem by your own, and if you feel any difficulty, you can ask. Thank you. Welcome back. Problem 1-76. This problem is taken from chapter number 1, Stress, and the book name is Mechanics of Material by R.C. Hibbeler. So statement is the hangers support the joist uniformly so that it assume the 4 nails on each hanger carries an equal portion of the load. Determine the smallest diameter of nails at A and B if allowable stress for the nail is 4 kSi. So shearing stress is 4 kSi. The hanger only supports the vertical load. So you can see this is the joist and these are hangers at A and B. Clear? And in this hanger we have 4 nails on each hanger, 2 on this side and 2 on other sides. Similarly here there are 2 nails on this side and 2 on other side. And this hangers only supports vertical reaction. Clear? And the loading on this joist is shown over here. So you have to determine the diameter of these nails and these nails, and the shearing stress is given as 4 kSi. So let's start with the solution. So what will be the first step is if you remove this support, hanger support at A, so it will be replaced by a vertical reaction which is represented as FA, and if you remove this hanger at B, so there will be a reaction force by this hanger on this joist will be FB, and we'll find this FA and FB by using equation of equilibrium. But before that, if you can see that if this load is like this here, so what we are going to do is that we will convert this load. This is a mixed loading, so we'll convert it into distributed load with a triangular load. So this distributed load will have magnitude 30 pounds per feet, while this magnitude of triangular load will be 40 minus 30 will be equal to 10 pounds per feet. So let me divide it. So I will take a horizontal line. So you can see this will be distributed load, and the magnitude here will be equal to 40 minus 30, which will be 10 pounds per feet. Okay, so when you convert this distributed load into a point load, so it will be equal to, this will be a point load, it will be equal to 30 into the length over which it acts. So 30 into 18 will be equal to 540 pounds. And when you convert this triangular load into a point load, so what we are going to is that it will be converted into point load since it is triangular. So it will be equal to 1 over 2 into the magnitude, which is 10, and the length over which act is 18 feet. So I will write 18, and that will give you 90 pounds. It's 90 pounds. Now the distributed load will act at a half of the distance of full length, which full length is 18. So 18 divided by 2 will be equal to 9 feet. And this triangular load will, when converted into point load, so it will act at a distance of L by 3 from this end B. So L is 18, so 18 by 3 will be equal to 6 feet. So 6 feet from the point B. So I will write it, this distance is 6 feet. Okay, and the remaining distance is 3 feet. Now we'll apply the equation of equilibrium. So what will be the equation of equilibrium? So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, the first moment will be this load, which is 540, and perpendicular distance is 9, and this will produce clockwise moment, so it will be negative. The second moment will be this load, which is 90 pounds, and perpendicular distance is 12, and this is also negative because it is clockwise. The third moment will be this FB into perpendicular distance is 18, and it is producing counterclockwise moment, so it will be positive. And the sum of all moment about point A must be equal to 0. So I will write 540 multiplied by 9, this is clockwise, minus 90 into 12 plus FB into 18 is equal to 0. So when you calculate it, you will get this 18 FB will be equal to 540 multiplied by 9 plus 90 into 12. So FB will be equal to 540 multiplied by 9 plus 90 into 12 divided by 18, and you will get this force, vertical force at point B will be equal to 330 pounds. Now you have this FB, you can find this FA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see FA plus FB minus 540 and minus 90 is equal to 0. So I will write FA plus FB, which is 330 minus 540 minus 90 is equal to 0. So FA plus 330 minus 630 will equal to 0. So FA minus 300 is equal to 0. So from here you will get this FA will be equal to 300 pounds. vertical force at point B is equal to 330 pounds there, and at A it is 300 pounds. And you can see this vertical force is applied reaction force of this hanger on this joist. As a result, joist will also, this is supporting this joist, so definitely this force will cause shearing stress in these nails. There are four nails at A there. So what we will do is that we will calculate the diameter. So I will write for nails at A, we know that allowable shearing stress is equal to shear force divided by vertical shear force divided by area of nails. So this is for single nail. Okay. Or you can also write it like this, that total area of shear force divided by total area, because this shear force is, these four nails are taking this shear force. Clear? So total area will be equal to FA divided by 4 times area of single nail is pi by 4 dA square. Clear? And what we will do is that we have been given as we are going to find dA. So dA square will be equal to FA divided by pi into T allowable. So you can put the value 300 divided by pi multiplied by allowable shearing stress is 4 ksi. So 4 into 10 raised to power 3 ksi will be equal to dA square. So from here you will get dA will be equal to 300 divided by pi multiplied by 4 into 10 raised to power 3 under the root, and you will get diameter of nail at A will be equal to 0.155 inch. So this is the diameter of nail at A. Similarly, you can find for nails at B, allowable shearing stress is equal to vertical shearing force at B divided by area of nails B. Since there are 4 nails, so I will write 4 multiplied by area of one nail is 4 pi by 4 dB square. And same you will get this dB square will be equal to FB divided by pi into the allowable. So you can just put the value of FB is 330 pounds. You can see this is 330 pounds divided by pi multiplied by pi allowable is 4 ksi. So 4 into 10 to the power 3, which is dB square. And from here you will get dB will be equal to under the root 330 divided by pi multiplied by 4 into 10 to the power 3. And you will get, when you solve this, you will get diameter of nails at B will be equal to 0.162 inch. So these are diameter of nails at A, and this is the diameter of nails at B, and which is the answer of this question. And that was all about this problem 1-76. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and hit the bell icon so that you can get notification about my latest videos. Please share these videos with your communities and help me in growing further. And if you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-85 that is taken from chapter number 1, stress, and book name is Mechanics of Materials by R.C. Hibbeler. So statement is the beam is made from southern pine and is supported by base plates resisting on the brickwork. If the allowable bearing stress for the materials are for pine it is 2.81 ksi and for brick allowable bearing stress is 6.70 ksi. Determine the required length of the base plates at A and B to the nearest 1/4 inch in order to support the load shown. The plates are 3 inch wide. So you can see this is the beam here that is made up of southern pine, and there is uniformly distributed load from one end till the over the whole length, that is 200 pound per feet, and there is a 6 skip load at a length of 5 feet from this point A, and there is a base plate between this beam and this bricks there. So you have to find the length of this base plate. So let's start with the solution. So first step is that if you remove this support at the brick, so there will be a reaction force. Let this reaction force is RA, and if you remove this bricks, so there will be a reaction force offered by this brick on this beam or base plate, which will be RB. Okay, now this 6 skip is equal to 6,000 pound. 6 skip is 6,000 pound, and when there is a uniformly distributed load of 200 feet, so when you convert this uniformly distributed load into a point load, so it will act at the half length of the beam, and this will be equal to 200 over the length which it acts. So total length is 13 feet. So 200 multiplied by 13 will give you 2,600 pounds feet, and it will act at the half. So total is 13. So it will be 6.5 from either sides. So this is 6.5 feet. Now we'll apply equation of equilibrium in order to find this RA and RB. So what will be the equation of equilibrium? So first equation of equilibrium, that sum of all moments about point A is equal to 0, and taking the counterclockwise movement as positive. So about this point A, the first movement will be due to this 6 skips or 6,000 pound load, and perpendicular distance is 5, and this is producing clockwise movement, so it will be negative. So I will write minus 6,000 into 5. The second movement is due to this load, and this is 2,600, and the perpendicular distance is 6.5, and this is producing clockwise, so it will be also negative. So I can write it minus 2,600 multiplied by 6.5. And the last load which is producing movement about point A will be RB into perpendicular distance is 10 feet, and this is producing counterclockwise movement, so it will be positive. So I will write plus RB multiplied by 10, and the sum of all movement about point A must be equal to 0. So from here we will get minus 30,000 minus this will be 16900 plus 10 RB is equal to 0. So what we will get is that 10 RB will be equal to 46,900, and this RB will be equal to, if you divide 10 on both sides, so you will get 4690 pounds. So this is the value of RB, reaction force by bricks at point B on the beam or base plate. Now you can find RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So RA is upward, so plus RA plus RB minus this 2,600 and minus 6,000, their sum must be equal to 0. So I can write RA plus RB minus 6,000 and minus 2,600 is equal to 0. So RA plus RB is 4690 minus 6,000 minus 2,600 is equal to 0. So when you calculate it, you will get RA will be equal to 3910 pounds. Now you have both RA and RB. So what we are going to do is that we will design this base plate. So what will be the parameters? So I will write the design must be based on the strength, and we will take the smallest strength, which is the strength of the pipe. So you have been given the allowable bearing stress of pine as well as for brake. So we will choose this value. Clear? This will be, and at point A, first we will calculate for A. So at A, we know that bearing stress is equal to bearing load over per unit area. So at point A, you can see this load is offered on this bearing plate. Clear? So we will write it as RA divided by area of base plate at A. And the bearing, we have taken the strength of pine. So strength of pine is 2.81 KSI. So 2.81 into 10 to the power 3 is equal to RA, which is 3910. And area of base plate, if base plate is like this, the width is given. This width is 3 inch. Clear? And this length is not given. This length, which is length A. So I can write area will be equal to LA multiplied by 3. Clear? So from here you will get LA will be equal to 3910 divided by 2810 multiplied by 3. And when you calculate it, it will be equal to 0.464 inch. And if you can see that if length is 1, we have been given that L should be nearest to 1/4 inch, which is equal to 0.5 inch. And if L is equal to half inch, it is 0.5. This is 0.25. Okay. As our value 0.4 is near to this 0.5, so L we use length of this base plate will be 1/2 inch. We can also write it 2/4 inch, which is again 1/2 inch. So length of this base plate is 1/2 inch. Now what we will do is that at point B, our base plate B, we know that stress is equal to RB divided by area. So from here the strength is 2.81 into 10 to the power 3 KSI. RB is calculated as 4690 divided by area of base plate for B will be LB into 3 inch. So again this length LB will be equal to 4960 divided by 2810 multiplied by 3. And when you calculate it, it will be equal to 0.556 since inch. So LB is equal to 0.556 inch. And we will take it nearest to 1/4 inch. So this is 1/4, this is 1/2, and 3/4 is 0.75. So our value is in between these two. So and for the closer, our safer design will be 3/4 inch. So we will choose LB is equal to 3/4 inch. 3/4 inch. Which is the answer of this question. So this length of this base plate should be half inch. Clear? And this length of this base plate should be 3/4 inch. And that was all about this problem 1-85. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 1-77 that is taken from chapter number 1, stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the tension member is fastened together using 2 bolts, one on each side of the member as shown. Each bolt has a diameter of 0.3 inch. Determine the maximum load P that can be applied to the member if allowable shearing stress for bolt is 12 KSI and allowable normal stress is 20 KSI. So you can see this is member 1 and this is member 2 that are held together by using a joint having bolt on one on each this side and other one on the other side. And this is exerted by a tensile load P. So you have to find the maximum load or allowable load P that can be applied on this joint or on this tensile tension member. So let's start with the solution. So what will be the first step is that first step is if you cut this or if you separate these members and draw the free body diagram, so it will be like this. Let me draw it first. This will be member. You can see this is a load P, clear, and this angle is 60 degree. So when you separate it, so you will be having a normal force perpendicular to this surface, clear, and this will act that we take it upward and there will be a shear force on this surface, clear. This will be a shear force. This is V and this will be equal to normal force. So we'll find this normal force and V in this member because you can see that this normal force, this shear force will tend to shear this bolt and this normal force will cause the tension in this bolt. So based on these two criteria, we'll find the maximum load that can be applied on P. So we will find this equation, N and V by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along Y direction must be equal to 0 and Y direction is taken in this because you can see you have N in this direction and V is in this direction. So what we are going to do is if you draw a line parallel to this 60 degree, clear? So if you draw a line parallel to this 60 degree. So this P will have two components, one along this axis which is equal to one along this axis and other along this parallel to this N. So this will let this is equal to X component and this is equal to Y component. So you can see PX will be equal to P cos of 30 degree, P cos of 60 degree, clear? And this PY will be equal to P sine of 60 degree. And you can see when you apply this equation, so you can see the force in this direction is N and other force in this direction is Py, which is equal to P sine of 60. Their sum must be equal to 0. So I will write N minus Py, which is P sine of 60 degree, clear, is equal to 0. So from here, this N will be equal to P sine of 60 degree, clear, and this P will be equal to N divided by sine of 60 degree. So that will be equal to 1.1547 N times N. Clear? So I will write it P will be equal to 1.547 times n. Let this is your equation number 1. Now we will apply another equation that sum of all component in x direction must be equal to 0 and force in this direction is taken as positive. So you can see V is in this direction and Px is in opposite direction. So plus V minus Px is equal to 0. So I will write V minus Px is equal to 0. So we know that Px is P cos of 60 degree. Clear? So from here that is equal to 0. So V is equal to P cos of 60 degree. Clear? And P will be equal to V divided by cos of 60 degree, and that will be equal to 2 times V. So I can write P is equal to 2V. That this is your equation number 2. Now you can see that here P is based on the normal force and here in 2 it is based on shear force. So what we are going to do is that we will first apply a criteria. We will apply criteria based on allowable shearing stress. Allowable shearing stress. So we know that allowable shearing stress is equal to V divided by area, since there are two bolts, one on this side and other one is on another side. So we will take this V. V is equal to we do not know V. So clear, I will write V divided by 2 bolts. So 2 multiplied by pi by 4. Diameter of bolt is given as 0.3 inch. So I will write 0.3 square. And allowable shearing stress for bolt is 12 ksi. So I will write 12 into 10 to the power 3 is equal to V divided by 2. Will cut with this. So we will get pi by 2 into 0.3 square. And from here we will get V is equal to 12 multiplied by 10 to the power 3 multiplied by pi by 2 into 0.3 square. And you will get the shear force comes out to be 1.696 kip. Now you have this V. So put it in equation number 2. Put in equation 2. So you will get P is equal to 2 times V, and that is equal to 2 multiplied by 1.696 kip. So you will get this P will be equal to 3.39 kip. Now this is the tensile load based on, it is based on shear stress, allowable shearing stress. Now what we will do is that we will use, this was the first criteria, we will use second criteria based on allowable normal stress. And we know that allowable normal stress is equal to normal force divided by area. Since there are two bolts, so I will write n divided by 2 multiplied by pi by 4. Diameter of bolt is given as 0.3, so 0.3 square. And allowable normal stress is given as 20 ksi. So 20 into 10 to the power 3 is equal to n divided by pi by 2, 0.3 square. So you will get this n will be equal to 20 into 10 to the power 3 multiplied by pi by 2 into 0.3 square. And you will get this n will be equal to 2.827 kip. So put n is equal to 2.827 kip in equation number 1. And what is equation number 1? P is 1.547 times n. So P is equal to 1.547 multiplied by n. So 1.547 multiplied by 2.827 kips. You will get P is equal to 3.26 kip. And this P is based on, it is based on normal stress. Yeah. So here you can see we have two values. One P is this one and another one is this one. So this largest load, I will write it over here. The largest tensile load, largest P which can be applied on this system is 3.26 kips. And which is the answer of our this question. Why we have selected this smaller one and called it as the largest load? Because you can see this load is less than this, so it will be safer. And if you put this P in this formula, and then shear force in this formula, so it will exceed the allowable, your shearing stress will be greater than this allowable shearing stress. So therefore for safer design we use P is equal to 3.26 kips. And that was all about this problem 1-77. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos in your community so that my channel may grow further and most of the students may learn from my videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 1-24 that is taken from chapter number 1, stress, and book name is Mechanics of Material by R.C. Hibbeler. And the topic is internal loading. This is a complex problem. So statement is determine the resultant internal loading acting on the cross section of semicircular arc at C. So we have to find the internal loading at C, which means that we have to find the normal force, we have to find the shear force, and we have to find the movement. So I will write it. What we have to find is we have to find internal loading, which means the shear force, normal force, and movement. So let's start with the solution. So first step is that if I remove this pin support at point A, so there will be a reaction force in y direction, which is AY. And if you remove this, there will be horizontal reaction force. Similarly, there will be a vertical reaction force if we remove this roller support. So that will be equal to BY. So what we are going to find this BY, and then we will cut this arc beam over here, and we will take this area in order to find internal loading at point C, which is VM and N. Clear? So let's find it. Now what we will do, you can see that there is a angle theta is given, which is theta, and the radius arc is given, and there is a uniformly distributed load on this arc. Clear? So what we will do is that we will take a small differential area element. For example, that this is theta, so this angle will be equal to d theta. Clear? And this is the portion over which we are analyzing the force. So since this is distributed force, so when we convert this distributed force into a point force, so since this is differential force, so this differential force will be equal to this W naught times this arc length, which will be equal to r theta, because this is r and this is d theta, so it will be W naught r d theta. Clear? Now you can see that this force is acting perpendicular to it, so it is also making theta with the horizontal. Clear? And this will have two components, one along x direction, clear, and one along y direction. So we'll find these two components. So this is theta, So this component will be equal to W naught R d theta into cos of theta, and this component will be equal to W naught R d theta into sine of theta. And you can see distance from this to this is R. So again, if I draw a perpendicular line from this point, so you can see this distance is R. So this distance will become equal to R cos theta, because this is theta angle. So this is R cos of theta, and this remaining distance will be equal to R minus R cos of theta. So R minus R cos theta is actually, if you take R common, so it will be 1 minus cos of theta. Clear? Now we are ready to apply the equation of equilibrium. So first equation of equilibrium is that sum of all forces along sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, these two forces are not producing moment because they are passing through it. So first force which is producing moment about point A is By into perpendicular distance is 2R, because this distance is R and this is R, so it will be 2R. And this is producing counterclockwise moment, so it will be positive. So I will write By into 2. So y should be on the lower side, on lower right side, By into 2. Now the second moment will produce due to this horizontal component, which is this one, and the perpendicular distance is this one. And this distance, you can see this, since this is R, so and this is theta, so this component will be equal to R sine of theta. So this component multiplied by this component will give you the moment, and this will produce clockwise moment, so it will be negative. So I will write minus W naught R d theta into cos of theta multiplied by R sine theta. And you can see that this is differential force. So for taking the net force over entire curved beam, I will integrate it, so it will be integral of 0 to pi. Clear? And same is the case, the third force will be this df sine theta, which is W naught R d theta sine theta, and now perpendicular distance is this one, which is R into 1 minus cos theta, and it is also producing clockwise moment, so it will be negative. So I will write minus integral of 0 to pi W naught R d theta into sine theta multiplied by R into 1 minus cos of theta, and that is their sum of all moment about point A is equal to 0. So if you simplify it further, so By multiplied by 2, and that will be, you can see W naught into R, and R, these are constant, so we will take it out, so it will be equal to minus W naught R square and integral of 0 to pi cos theta into sine theta d theta. And same here, we will get W naught R into R is common, so W naught R square will be common, and we will left with 0 to pi, and it will be sine theta into 1 minus cos theta into d theta is equal to 0. Now further simplify it, By into 2 is equal to By into 2R, so you have to multiply it with R, By into 2R. So By into 2R minus W naught R square integral of 0 to pi sine theta into cos theta into d theta minus W naught R square, and we will have integral of 0 to pi sine theta into d theta minus integral of 0 to pi sine theta into cos theta d theta is equal to 0. Okay, so we will get By into 2R minus W naught R square into integral of 0 to pi sine of theta into cos of theta d theta minus this will be W naught R square integral of 0 to pi sine theta into d theta, and that will be plus W naught R square integral of 0 to pi sine theta into cos theta d theta is equal to 0. So you can see this will cancel with this, and we will left with By into 2R minus W naught R square integral of 0 to pi sine theta into d theta is equal to 0. And By into 2 minus W naught R square, clear, and that will give you integral of this sine theta will give you minus cos of theta from 0 to pi. So we will get, so this By into 2R minus W naught R square, and that will be minus cos of pi, minus minus will be plus cos of 0 degree is equal to 0. So By into 2R minus this will W naught R square, and this is 2. You can calculate it, this is 2. So By into 2R minus 2 W naught R square is equal to 0. So from here, you will get By is equal to W naught into R. Now you have this By, clear? So what we will go is that we will section this beam at this point, and we will concentrate on this portion. So I have already taken this section. So what we will do is that you can see you have By is this one, which is By is equal to W naught into R. So when you cut it, so you will be having a normal force at point C, like this is NC. You will be having a shear force which is equal to VC, clear? And you will be having a moment which will be equal to MC, and this is the origin or center point O. So we will find this MC, NC, and VC. What we will do is again that you can take the differential, that this is the theta. So we will take a differential element. This will be equal to d theta. So this differential element will be having a differential force which will be perpendicular to this here, and this df will be equal to W naught R into d theta. And again you can see the total angle is theta. So this will also make, it will have two components. One is this one, another one is this one. So this component will be equal to W naught R d theta into cos of theta, and this will be equal to W naught R d theta into sine of theta. Okay, now we'll apply equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see one force which is NC is in positive direction, and the other component of this force in this negative direction. There is no other horizontal force here, sum must be equal to 0. So I can write NC minus W naught R cos of theta into d theta. Since this is differential equation, so if I integrate from 0 to pi, clear, from 0 to pi by 2, sorry, pi by 2, so we will get a net force, horizontal force acting on the system. So I will integrate it from 0 to pi by 2, okay, is equal to 0. So from here NC will be equal to integral of W naught R cos of theta into d theta, and 0 to pi by 2 it will be equal to W naught R integral of 0 to pi by 2 and cos theta into d theta. So when you calculate it, you will get 1 from this integral of pi by 2, integral of cos theta into d theta pi by 2, and you will get NC will be equal to W naught into R. Clear? Now we'll find this VC by using another equation of equilibrium, and that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force upward is W naught into R, the second force is VC, and the third force is this downward force. So minus W naught R sine of theta into d theta. And since this is differential force, so for entire length from 0 to pi by 2, we will get, if we integrate this force, we will get a net vertical force. So I will write integral of 0 to pi by 2 is equal to 0. Now W naught into R plus VC, and this is minus W naught R integral of 0 to pi by 2 sine of theta into d theta is equal to 0. And you will get 1 from this as well. So you will get W naught into R plus VC minus W naught into R is equal to 0. So from here, VC is equal to 0. It means that there is no shear force at point C. And the last thing is that we will find this moment NC. So what we will do is that we will apply equation that sum of all moment about point A is equal to 0, taking the counterclockwise moment as positive. Since this force is passing through point A, it is not producing moment, clear? And this force, net force, is also passing through point A, it is not producing moment. So only moment is produced by this By into perpendicular distance is R, and NC into perpendicular distance is R. So I will write NC into R, this is producing clockwise, clear? NC into R, this is clockwise, plus this By into perpendicular distance is R, and this is counterclockwise, so it will be plus. So By, which is W naught into R, and perpendicular distance is R, plus this MC, which minus MC, which is clockwise, minus MC. Their sum must be equal to 0. So NC is W naught into R, so it will be minus W naught R square, plus this will be W naught R square minus MC is equal to 0. So it means that moment at point C will be also equal to 0. So you can see we have found internal loading NC, VC, and MC at point C. Clear? And that was all about this a little bit complex problem 1-24. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching me and supporting me. Welcome back. Problem 1-92. This problem is taken from chapter number 1, that is stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is, if allowable bearing stress for the material under the support at A and B is 1.5 megapascal, determine the maximum load P that can be applied to the beam. The bearing plates at A dash and B dash have square cross section of 150 by 150 millimeter and 250 millimeter by 250 millimeter respectively. So you can see this is the beam, clear, having support A and B, and there is a bearing plate A dash and B dash at this support. There is a uniformly distributed load over length of 1.5 meter, and the cross sectional area of A dash is 150 by 150 millimeter, and at B it is 250 by 250 millimeter. So you have to find the greatest load or maximum load that can be applied on this beam. So let's start with the solution. So what will be the first step? The first step is that if you remove this support at point A, so you will be having a reaction force. Let this reaction force is NA, that is offered by the support on the beam. And if you remove this support at B, so it will offer a vertical reaction force on this beam, and let this will be NB. So we'll find this NA and NB by using equation of equilibrium. So what will be the equation of equilibrium? So first equation of equilibrium is that sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. So you can see here there is a uniformly distributed load. So when converted into a point load, so it will be 40 multiplied by the length over which it acts, and it will act at a distance half of this length, which is 1.5 divided by 2 is 0.75 meter. So first we will convert this uniformly distributed load into point load, so it will be equal to 40 multiplied by the length over which it acts, and the unit will be kilonewton, and that will act at half of this 1.5. So this distance will be 0.75 meter. Okay, now we apply equation of equilibrium about point A, sum of all moment about point A. So first moment about point A is due to this NA, and perpendicular distance is 3 meter, and this is producing counterclockwise moment, so it will be positive. So I will write NB multiplied by 3 meter. The second moment that is produced due to this uniformly distributed load, when converted into point load, it will be this one, and perpendicular distance is 0.75, and it is also producing counterclockwise moment, so it will be positive. So I will write 40 multiplied by 1.5, and the perpendicular distance is 0.75. The last moment that is produced due to this P load and perpendicular distance will be 4.5, and this is producing clockwise movement, so it will be negative. So I can write minus P times 4.5 is equal to 0. So from here you will get 3NB. The second term will give you plus 45, and minus 4.5 times P is equal to 0. So 3NB is equal to 4.5 times P minus 45. And if you divide 3 on both sides, so you will get NB will be equal to 1.5 P minus 15. Clear? So this is the vertical reaction force of the support B on the beam. Clear? Now we'll find this reaction force at point A. So for that I will apply another equation of equilibrium, that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So first moment will be due to this force, and now perpendicular distance is this one, which is 3.75, and it is producing counterclockwise moment, so it will be positive. So I will write 40 multiplied by 1.5, and perpendicular distance is 3.75. The second moment about point B is due to this NA, and perpendicular distance is 3 meter, and this is producing clockwise moment, so it will be negative. So I will write minus 3 times NA, and the last moment is due to this P load, and perpendicular distance is 1.5, and this is producing clockwise movement, so it will be also negative. So I will write minus P times 1.5 is equal to 0. So what we will get here is the first term will give you 225 minus 3 NA minus 1.5 times P is equal to 0. So 3 NA will be equal to 225 minus 1.5 times P. And again, if you divide 3 on both sides, so you will get NA will be equal to 75 minus 0.5 times P. And this is the vertical reaction offered by support A on the beam. Now we have these two beams. So according to Newton law, the same load will be transferred to this bearing plate here at point A and at point B. So what we will calculate the P load for plate A. We will calculate P load for plate at A dash. We know that allowable bearing stress at plate A, let me correct it, this is allowable bearing stress at plate A will be equal to normal load A divided by the bearing area of A dash, A dash, clear? So we have normal load is 75 minus 0.5 times P, area of bearing plate is given in meter, it is 0.150 multiplied by 0.150, clear? And we know that allowable bearing stress for this material is given as 1.5 megapascal, so I will write 1.5 into 10 to the power 6 is equal to 75 minus 0.5 times P divided by 0.150 multiplied by 0.150. Okay, so what we will get is that 1.5 multiplied by 10 to the power 6 multiplied by 0.150 whole square is equal to 75 minus 0.5 times P. So 0.5 times P will be equal to 75 minus this whole term, which is 1.5 into 10 to the power 6 multiplied by 0.150 square. And if you divide 0.5 on both sides, so you will get P will be equal to 75 minus 1.5 into 10 to the power 6 multiplied by 0.150 square divide by 0.5. And after calculation, you will get P will be equal to 82.5 kilonewton. Now this is the load that will be acting on the beam and that will be there for plate at A dash. What we are going to do is that we will find P load for plate at B dash. That will be equal to allowable bearing stress will be equal to normal load at bearing plate B divided by area of bearing plates. So normal load at B is 1.5 times P minus 15. Since this load is in kilonewton, let me check it. This load is in kilonewton, so this unit will be also kilonewton. Clear? And I forget to put 10 to the power 3 to convert it into Newton. So you have to multiply 10 to the power 3. And again, this will be equal to divide by 10 to the power 3. Clear? And here you will also have 0.5 divided by 10 to the power. You can see, here also it is divided by 10 to the power 3 and 0.5 into 10 to the power 3. So you will get, so kindly make this correction 0. Here 10 to the power 3 to convert it into Newton. And area of this bearing plate at B is 0.250 square meter. And 250 multiplied by 0.250. And allowable bearing stress is 1.5 megapascal, so 1.5 into 10 to the power 6 is equal to 1.5 times P minus 15 into 10 to the power 3 divided by 0.250 square. So from here you will get 1.5 multiplied by 10 to the power 6 multiplied by 0.250 square divided by 1000. 10 to the power 3 will be equal to 1.5 times P minus 15. So what we will get is that 1.5 times P is equal to 1.5 into 10 to the power 6 multiplied by 0.250 square divided by 1000 plus 15 is this one. If you divide 1.5 on both sides, so you will get the value of P, which will be 72.5 kilonewton. And this is the value of load that is applied to the beam and that this plate B can bear. Clear? So we have to choose one value. So we will choose one value of P. So choose that is maximum load that can be applied on the beam, that will be 72.5 kilonewton, which will be the answer of this question. Now, most of students ask why you choose the smallest, because in question it is given that choose the largest. So this load is safer. So if you apply this load, this beam will, the load in plate B will be less than 82.5. But if you apply this load, so it will, this P will be greater than the sigma B allowable bearing stress in plate B will be greater than the given allowable stress. That's why we choose the smallest one. And that was all about this problem 1-92. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-88 that is taken from chapter number 1, Stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the compound wooden beam is connected together by bolt at B, assuming that connection A, B, C, and D exert only vertical forces on the beam. Determine the required diameter of bolt at B and the required outer diameter of its washer. If allowable tensile stress for the bolt is 150 megapascal and allowable bearing stress for the wood is 28 megapascal. Assume the hole in the washer has the same diameter as the bolt. So you can see these are compound beams that are connected together by a bolt at B, and this reaction at A, B, C, and D only exert vertical force. All other loadings are shown over here. Clear? So you have to determine the diameter of this bolt. Clear? Diameter of this bolt and the washer that is used, outer diameter of the washer that is used in this bolt. So let's start with the solution. So as this is a compound beam, so what we will do is that we will first draw the free body diagram FBD of member or beam CD. So you can see this is beam CD. So there is a vertical reaction force of D at D, which will be FD. There is this load, this load. Now the bolt will exert a load that will acting downward on this, and this reaction force by the C will be upward. So we will draw its free body diagram. So let me draw it first. Let this is the beam. Here you have to draw it. This is point C. So we have FC that will acting upward. This is C point. This is your D point here. So your force D will be also upward. FD. There is a 2 kilonewton load acting at a distance of 1.5 meter from this. So this distance is 1.5 meter. There is another load which is also 1.5 kilonewton and acting at a distance of 1.5 meter from the 2 kilonewton load. Now this is point B. Clear? So the load that is acted upon by this, the bolt X on this member or beam CD is FB. The distance between FC and FB is also 1.5 meter, and from B till this node is also 1.5 meter. Now we'll apply equation of equilibrium in order to find this FB and FC. So what actually we are interested to find out this load FB. So what we are going to do is that we will apply equation of equilibrium that sum of all moment about point D is equal to 0 and taking the counterclockwise moment as positive. So first moment about point D will be equal to this force FB and perpendicular distance is this sum of all this is 4.5 meter and this is producing counterclockwise moment, so it will be positive. So I will write FB into 4.5. The second moment that is produced due to this 1.5 kilonewton load and the perpendicular distance is 3 clear meter, and this is also producing counterclockwise moment, so it will be positive. So I will write plus 1.5 into 3. The third load which is producing moment is this 2 kilonewton and perpendicular distance is 1.5 about point D and it is producing counterclockwise moment, so it will be positive. So plus 2 into 1.5. And the last force which is producing moment about point D is FC, and this whole perpendicular distance is 6. This distance is 6 meter and this is producing clockwise moment, so it will be negative. It will be negative. So I will write minus FC multiplied by 6 is equal to 0. So from here this will be equal to 4.5 times FB minus 6 times FC, and these two terms, this and this term will give you minus plus 7.5. When move toward right side, it will be minus 7.5. That this is your equation number 1. Now what we will do is we will take the free body diagram of this beam AB. So you can see there is a vertical reaction force. The C will now act downward on this and FB will be also upward on this, and there is a load. So we will draw this free body diagram. So I will write free FBD of member AB. So let me draw the free body diagram again. So you can see this is point A. So you will be having a reaction, vertical reaction force, which is FA. There is a 2 kilonewton load, 3 kilonewton load. You can see this is 3 kilonewton load that is acting at a distance of 2 meter from this side. Let this is point C, clear. So at C you will be having a force that will be acting downward. Why? Because you can see that this force at C will be upward. So as there is Newton third law, it will be acting downward. So this is FC, clear. And same FB here is downward, clear. So here it will be upward. So let this point is your point B. So here it will be upward, FB. Clear. And all the distance between these two forces are 2 meter, clear. And from C to B it is 1.5 meter. Now we will apply equation of equilibrium. So the equation of equilibrium which we will apply is sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, one moment that is produced due to this FB and perpendicular distance is 2 plus 2 plus 1.5 is 5.5, and this is producing counterclockwise moment, so it will be positive. So I will write FB into 5.5. Clear. The second moment that is produced due to this FC and perpendicular distance is 4. This is 2 and this is 2. So it will be 4 meter and it is producing clockwise moment, so it will be negative. So I will write minus FC multiplied by 4. The third moment will be produced due to 3 kilonewton load and perpendicular distance is 2 and this is producing clockwise, so it will be also negative. So I will write minus 3 into 2, and the sum of all moment about point A must be equal to 0. So what we will get is 5.5 times FB minus 4 FC is equal to 6. So from here you will get 4 FC is equal to 5.5 times FB minus 6. And if you divide 4 on both sides, so you will get 5.5 divided by 4 FB minus 6 divided by 4. And that will give you 5.5 divided by 4 will give you 1.375 times FB, and 6 divided by 4 is 1.5. And this is your equation number 2. Now what we will do is that put equation 2 in equation number 1, which is this one. You can see, so 4.5 times FB minus 6 times FC is 1.375 FB minus 1.5 is equal to minus 7.5. So 4.5 FB minus 6 multiplied by 1.375 is 8.25 times FB plus 6 multiplied by 1.5 is 9 is equal to minus 7.5. Clear? So minus 4.5 minus 8.25 FB is minus 3.75 FB is equal to minus 7.5 minus 9, which is equal to minus 16.5. And if you divide minus 3.75 on both sides, so you will get FB is equal to 4.4 kilonewton. So this is the force in the bolt. Now what we will do is that put FB in equation number 2. So you will get FC will be equal to 1.375 times FB is 4.4 minus 1.5, and you will get FC will be equal to 4.55 kilonewton. Okay, since we are in need of force in this bolt, so now we will calculate the diameter of this bolt. So what actually I will write is we have been given allowable stress for this bolt is given as, which is equal to FB divided by area of bolt. So FB is 4.4 kilonewtons, 4.4 into 10 to the power 3. Area of bolt is pi by 4, diameter of bolt square. Clear? So allowable stress for the bolt is 28 megapascal. So I can write it 28 into 10 to the power 6 is equal to 4.4 multiplied by 10 to the power 3 divided by pi by 4 dB square. So from here you will get dB square is equal to 4.4 multiplied by 10 to the power 3 divided by pi by 4 into 28 10 to the power 6. And if you take square root on both sides, so you will get the diameter of bolt will be equal to it will be 0.00611 meter. Our diameter of bolt will be equal to 6.11 millimeter. So this is the answer of our first part. Now we'll move towards second part, and in second part we have been asked to find the outer diameter of washer. So for washer, so you can see if this is a circular washer, clear, the inside diameter will be diameter of bolt. So this will be dB, and we will need diameter of washer, outer diameter. Clear? This is dW. So bearing stress, you can see that this washer is in contact with this wooden piece, so bearing pressure will be there. So this allowable bearing stress for this wooden will be equal to FB divided by area of washer. Clear? So FB is 4.4 kilonewtons, so 4.4 into 10 to the power 3, and area of washer is pi by 4 dW square minus dB square. So diameter of bolt in meter is 0.00611, so 0.00611 square. And allowable stress for the wood is 28 megapascal. Okay, so 28 megapascal. So 28 into 10 raised to power 6 is equal to 4.4 into 10 raised to power 3 divided by pi by 4 into dw square minus 0.00611 square. So when you calculate it, dw, you can now find it, dw square will be, or dw, when you calculate it, it will be equal to 0.0154 meter, or that will be 15.4 millimeter. Also make a correction that here allowable tensile stress for the bolt is 150 megapascal. So I will write it as 150 megapascal. Correct it, 150 megapascal. So 150, here this will be also 150, and you will get this diameter of bolt. So make this correction, and that was all about this problem 1-88. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-89 that is taken from chapter number 1, stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the required minimum thickness T of the member AB and edge distance B of the frame if P is 9 kips and the factor of safety against failure is 2. The wood has a normal failure stress 6 ksi and shear failure stress of 1.5 ksi. So you can see this is the member AB and the thickness is not known. We have to find this thickness, and this B distance, the load acting or this frame is P, which is 9 kips. The normal failure stress is 6 ksi and shear failure stress is 1.5 ksi. So you have to determine this thickness T and this B of the frame. So let's start with the solution. So first we will find internal loading. So let me write it first. The normal force developed in member AB can be determined by considering the equilibrium at joint A. So what we will do is that we will take this joint A and we will draw the free body diagram and we will find the force AB. So let me take this. This is member AB and this is member AC. Yeah. Okay. So this is member AC and this is member AB. This is B. This is your point A and this is your point C. At A we have vertical load of P, which is given as 9 kips. So 9 kip. So when you cut it, section B, so you'll be having a reaction force acting on section AB. Let this force is FAB, and when you cut it, you will be having a normal force, normal axial force, which will be equal to FAC. Now, if I take a horizontal line from this, so it will be this will be your x-axis, and this will be your vertical will be your y-axis. And you can see here this makes an angle of 30 degree. So again, if I draw a horizontal line, so this will be also 30 degree. So it's called alternate angle. So this angle will be 30 degree. Here, this angle is also 30 degree. Now, if I take the center line of this member and this member, so we will apply equation of equilibrium in order to find the FAB and FAC. So this FAB will have two components. This FAB will have two components, one along x-axis and other along y-axis. Clear? So we will apply equation of equilibrium that sum of all forces along x direction must be equal to 0 and upward force is taken as positive. So you can see this force will have one component. This FAB is like this. So it will have one component this and other. So horizontal component will be equal to FAB cos of 30 degree. And since it is toward positive side, so I will write it FAB cos of 30 degree. And same is the case, this FAC will have two components. One is this one, another one is this one. And this component is FAC cos of 30 degree. And it is toward negative direction. So I will write minus FAC cos of 30 degree. And their sum must be equal to 0. So it means that FAB cos of 30 degree is equal to FAC cos of 30 degree. So cos of 30 will cancel each other. So FAB will become equal to FAC. Okay, now we'll apply another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force which is downward is minus 9. So I will write minus 9. This component, the vertical component of this force, which was FAB sine of 30 degrees upward, and similarly FAC sine of 30 degree is also upward. Their sum must be equal to 0. So plus FAB sine of 30 degree plus FAC sine of 30 degree is equal to 0. Now you can see FAC is equal to FAB, so I will replace this FAC with FAB. So it will be FAB sine of 30 degree plus FAB sine of 30 degree minus 9. So 2 times FAB sine of 30 degree is equal to 9. And when you divide it, FAB will be equal to 9 divided by 2 sine of 30 degree. So you will get FAB will be equal to 9 kip. Clear? So let me write it. FAB is equal to FAC is equal to 9 kip. Now we have this force in member AB and AC. So what we are going to do is that you can see that this member is over here. So due to this force FAB, it will be having two components, one along x-axis, y-axis, and another along x-axis. So this force will cause the shearing in this region, So we'll find that. So let me draw its free body diagram. So I will write, if I take that portion, or if I take the member AB and joint B using joint B of member AB So this is joint B, clear? So you can see you will be having this FAB in this direction. FAB will be like this. This is FAB. So it will be having two components. One is this one and other one is this one. Clear? This is angle 30 degree. So this component will be equal to FAB cos of 30 degree and this component will be FAB sine of 30 degree. So we'll find this FAB cos 30. So what I'm going to say is that this is the member AB. Clear? And this was the joint like this. This is the member. So force in this member was 9 kip. 9 kip. And it will having two components. This is 30 degree. Clear? And this is your point B. So at point B, you can check it that it will have a reaction force in horizontal as well as in vertical direction. So I will write this horizontal component will be FBX and the vertical component will be FBY. Now, what we are going to do is that we will find this FBX and FBY by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see we will need only this horizontal reaction force because it is creating shear at this point. Clear? At this point. So we'll find this by using equation of equilibrium which I have written. So FBX minus the horizontal component of this which is 9 cos of 30 degree. So I will write it minus 9 cos of 30 degree is equal to 0. So from here FBX component will be equal to 7.794 kip. Now this horizontal force is actually, you can see it will exert by this member over here. As a result, this member, this force, horizontal force will produce shear in this area. So if I draw a free body diagram of that portion, so that this is the portion where you have a net force of FBX is applied, and due to that we have a shear V which is taken as VA-A. What is A-A? So let me show you that if you take this line, so this is the plane AA where you cut it, and we have drawn the free body diagram over here. Okay, so FBX is 7.794 kips. So by using equation of equilibrium, sum of all forces along x direction must be equal to 0 and force in this direction is positive. So VAA minus 7.794 is equal to 0. So VAA means shear force, horizontal shear force will be also equal to 7.794 kip. Now you have both this normal force in member AB and shear force. So what we are going to do is that we will find allowable stresses. So let me write it: allowable normal stress and shear stress. How we'll find that? We have been given this normal failure stress and shear stress. We also know the factor of safety. So using these values, we will first calculate allowable shearing stress. So allowable normal stress. So allowable normal stress is equal to failure stress divided by factor of safety. Clear? So failure stress is 6 and factor of safety is 2. So it means that allowable normal stress is 3 ksi. And same is allowable shear stress is equal to failing shear stress divided by factor of safety. So failing shearing stress is 1.5 divided by 2 is 0.75 ksi. So now we will use these two to find the force in AB, and we will find the distance B. So first we know that allowable normal stress is in member AB is FAB divided by area of AB, that is equal to 3 into 10 to the power 3, and FAB is 9 ksi. So I will write it 9 into 10 to the power 3. Now what is area of AB? So you can see the thickness is this one which is not known and the width is 3. So it's actually T by 3 inch. So we will use this area is 3 multiplied by T. Clear? So from here you will get T will be equal to 9 into 10 to the power 3 divided by 3 into 3 multiplied by 3, which is equal to 1 inch. So this is the answer of our first part. Now we'll find this tar allowable is given as VAA divided by area of AA. So let me show you. You can see here shear stress is VAA and the area is this B. Clear? And the area is B multiplied by this thickness. You can see this is 3. Sorry, this is the length B and this is the width 3 inch. And this will be the shearing area. So it will be 3B. So put the values. VAA is 7.794 divided by 3B is equal to allowable shearing stress, which is 0.75 into 10 to the power 3. So what we will get is that B is equal to 7.794 and there is 10 to the power 3 because K is pound kip. So 10 to the power 3 divided by 3 into 0.75 into 10 to the power 3. So what you will get is B is equal to 3.46 inch. So that is the answer of our second part. So I will conclude that this thickness T is equal to 1 inch and this B is equal to 3.46 inch, which is the answer of this question. And that was all about this problem 1-89. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 1-93 that is taken from chapter number 1 stress and book name is Mechanics of Material by R.C. Hibbeler. So statement is the rod AB and CD are made of steel. Determine their smallest diameter so that they can support the dead load shown. The beam is assumed to be pin connected at A and C. Use LRFD method where the resistance factor for steel in tension is 0.9 and the dead load factor is 1.4. The failure stress is 345 megapascal. So you can see this is beam AC that is supported by two rod AB and CD that are made of steel. The dead load is shown over here. So you have these are the pins supported at point A and C. So using load and resistance factor design method. So you have to calculate the diameter of rod AB and this diameter of rod CD. So let's start with the solution. So you can see that due to this dead load here, there will be a tensile stress in rod AB and CD. As a result, this rod exerts a vertical force FAB on this beam and FCD on this beam. Clear? So we'll find this FA and FCD by using equation of equilibrium. So it is better to draw a separate field bar diagram for saving time. I am already drawing over here. So this is FAB, which is the force that is exerted by this rod on this beam, and this is FAC. So we'll find this FA and FAB and FAC by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, taking the counterclockwise moment as positive. So about point A, the first force which is producing moment is FAC, and perpendicular distance is 3 plus 3 plus 2 plus 2, which is 10. And this is producing counterclockwise moment, so it will be positive. So I will write FAC multiplied by 10. The second moment which is produced by this 5 kilonewton load and perpendicular distance is this 7 meter, and this is producing clockwise, so it will be negative. So I will write minus 5 into 7. The third load which is producing moment is 6 into perpendicular distance is 4 meter, and this is producing clockwise, so it will be negative. So I will write minus 6 into 4. And the last force which is producing moment about point A is 4 into perpendicular distance is 2, and this is producing clockwise, so it will be negative. So minus 4 into 2 is equal to 0. So we will get 10 FAC is equal to 67.67 kilo Newton. And from here, this FAC will be equal to 6.70 kilo Newton. Now this is FAC, so we can find FAB by using another equation of equilibrium is that sum of all moment about point C is equal to 0, and taking the counterclockwise moment. So you can see that about point C first moment is FAB and perpendicular distance is 10. This is producing clockwise moment, so it will be negative. So I will write minus FAB into 10. Clear? The second moment will be 4 into perpendicular distance is this 8, and this is producing counterclockwise moment, so it will be positive. So I will write 4 into 8. This force is producing 6 multiplied by 6, and that is counterclockwise, so it will be positive. So I will write plus 6 multiplied by 6, and the last force is 5 into perpendicular distance is 3, and this is also counterclockwise. And the sum of all moment about point C is equal to 0. Okay, so from here, when you calculate it, you will get FAB is equal to 8.30 kilo Newton. You can also find this by using this equation that sum of all forces in y direction must be equal to 0, and upward force is taken as positive. So FAB minus 4 kilonewton minus 6 minus 5 plus 6.70 is equal to 0. So FAB is equal to minus 15 plus 6.70 is equal to 0. So FAB will be equal to 8.30 kilonewton. So you can use any of this in order to find this, but this one is the simplest one. Now we have FAB and FAC. We have been given as factored load. So we'll find factor load because you can see that we have been given dead load factor is 1.4. So this load FAB will be increased by 1.4 times. So 1.4 multiplied by FAB is 8.30. So this load will be increased. So it will be equal to 11.62 kilonewton. And similarly, FAC will be also increased by 1.4 because the dead load factor is given. So we have to multiply it. So this will be equal to 9.38 kilonewton. Now using LRFD, load and resistance factor design method. Clear? By using this, we know that this factor which is given as pi 0.9. So this 0.9 into 0.9 into failure will be equal to for rod or for rod AB. 0.9 into failure will be equal to FAB because this is in tensile. This is given resistance factor for steel in tension is 0.9. So this will be equal to area of AB. Clear? Now what we will do is that from here 0.9 failure stress is given as 345 megapascal. So multiply by 345 into 10 to the power 6. Clear? Is equal to FAB. FAB is 11.62 and 10 to the power 3 will convert it into Newton divided by area. So pi by 4 DAB square. Clear? So what we are going to calculate is we are going to calculate DAB. So DAB square is equal to 11.62 into 10 to the power 3 divided by 0.9 into 345 multiplied by 10 to the power 6 multiplied by pi by 4. And if you take square root on both sides, so you will get DAB will be equal to 0.00690 meter. Or DAB will be equal to 6.90 millimeter. So this is the diameter of rod AB. Now for rod AC, we will get 0.9 multiplied by failure is equal to FAC divided by area AC. So definitely you will get this will be equal to FAC divided by area AC, which is pi by 4 DAC square. So from here you will get DAC square will be equal to FAC divided by 0.9 multiplied by failure stress into pi by 4. And taking the square root on both sides will give you FAC is 9.38. So 9.38 into kilo. So 10 to the power 3 divided by 0.9. Failure stress is 345 megapascal. So 345 into 10 to the power 6 pascal and pi by 4. So from here this DAC will be equal to 0.00620 meter, or this DAC will be equal to 6.20 millimeter, which is the diameter of rod AC. So this is diameter of rod AB and this is diameter of rod AC. And that was all about this problem 1-93. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notifications about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 6-139 that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the curved beam is subjected to a bending moment of 40 pounds into feet. Determine the maximum bending stress in the beam. Also sketch a two-dimensional view of the stress distribution acting on section AA. So you can see this is the curved beam, clear, that is acted upon by this moment M, and which is given as 40 pound into feet. So due to this moment you have to determine the maximum bending stress in the beam. So let's start with the solution. So here you can see I have written the formula that is used in curved beams. The first one is this one, second one is this one, and third one is this one. So in this formula, sigma is equal to normal stress or bending stress. M is the moment that is given. What is this capital R? So capital R is distance from this center of curvature till to the point where its neutral axis lies. So this distance is R. We will find this, clear. What is this small r? So small r is distance from the center of this curvature to the any point. It can be here, it can be here, it can be anywhere. So where you want to find the stress, and this r dash will be equal to distance from this center of curvature till the centroid of this section. So we will find them each by each. So let's start with the finding radius r dash, which is the distance. I will write it distance from center of curvature to the centroid of section, clear. So we'll find that. What is the center of curvature? So you can see this arc is bent in a curve and it is forming a arc having radius is 3 inch. So this is center of curvature. So what if I extend this center of curvature, our x is passing through this center of curvature, and let's take this as a reference line in order to find the centroid of this section, which is T section. So for that I will write the formula. This r dash will be equal to sum of y dash into a divided by sum of area. So this is your first this first rectangle is your part 1 and this second rectangle is your part 2. So from this we will get y1 dash into a1 plus y2 dash into a2 divided by sum of area, which is equal to a1 plus a2. And what is area a1? So I will write it. A1 is equal to, you can see here, this is 2 and this is 0.5. So 2 multiplied by 0.5 square inch. What is area a2? So area a2 is, you can see this height is 2 and this width is 0.5. So it will be again 2 into 0.5 square inch. Now what is y1 dash? So y1 dash is distance from this reference line or from the center of curvature till the mid of this first section. So you can see we have to find this distance, which is y1 dash. And this y1 dash, you can see that this distance is equal to, this is 3 inch. So 3 inch plus 2 inch, 5 inch plus 0.25. So this will be equal to 5.25 inch. So I will write it, y1 dash is equal to 5.25 inch. 5.25 inch. Now what is y2 dash? So y2 dash is distance from this centroid of section of curved beam till the mid of second section. So this distance is already, you can see this is already 3, clear. So 3.5 of 2 is 4. So this distance is 4 inch. And I will write it here. This is equal to y2 dash y2 dash and this, that is equal to 4 inch. Okay, now 4 inch. Now I put all these values in this formula. So r dash will become equal to y1 dash is 5.25 multiply by 2 multiply by 0.5, which is area A1, plus y2 dash is 4 inch into area A2, which is 2 multiplied by 0.5 divide by, I will write 2 multiplied by 0.5 plus 2 multiplied by 0.5. So when you solve this, you will get this r dash, which is distance from center of curvature to the centroid of section, comes out to be 4.625 inch. This is this r dash. Okay, now I will remove these things. So in order to have a clear understanding about what is r dash, so let me plot it. So r dash is distance from neutral axis till the distance from the center of curvature till this centroid. This is the centroid. So this distance is r dash. Distance from the center of curvature till the centroid of this section is r dash, and this r dash is 4.625 inch. Now we will move toward finding second term, which is capital R. So capital R, you can see it is equal to area divided by integral of dA over R for the entire area. So what is the area, total area? So total area A is equal to A1 plus A2, which is equal to 0.5 multiplied by 2 into 0 plus 0.5 multiplied by 2. So 1 plus 1 will give you total area will be equal to 2 square inch. Okay, now the second term here is this one. So I will write integral of dA over R for the entire area. So you can see these two portions are rectangle 1 and 2, and they are away from this reference line. So for that we will take the value of this from this table. Since our shapes are rectangle, so this line is the axis passing through curvature. So you can see that this from this axis the rectangle is locating at a distance of r1 from this and r2 from this, having width or breadth is equal to b. So as we have two triangles, so first the formula is, the general formula will be equal to b into ln of r2 over r1. But as we have two sections, so I will write integral of dA a over r. This is not dA, this is a. This is a. Okay. For the first section, let me show you here. You can see this is the centroid axis passing through this center of curvature. So for that, for section 2, let's take section 2 first. So for section 2, this will be equal to R1. So R1 is 3 inch. You can see 3 inch, and R2 is distance from this center of curvature till the top layer. So this is equal to 2. 2 plus 3 is 5. So R1 is 3 and R2 is equal to 5. So I will write it, and the width is 0.5 for this. So I will write the B is equal to 0.5 ln of R2 was 5 and R1 was 3. So this is for first section. Now we will move toward the second section, which is this one. So for that, R1 will be this one, which is equal to 5, and R2 is this one, which is equal to 5.5 inch. And breadth here, you can see the breadth of this section is 2. So I will write plus 2 into ln of 5.5 divided by 5. So when you solve this, this will give you 0.44603 inch. Now you have both the values. You can just plug it in this formula, which is equal to R and area is 2 divided by this integral of dA over r for the entire area is 0.44603. So when you solve this, you will get this 4.480 inch. Now what is this r? It is the distance from the centroid till the neutral axis of this curved beam, because in curved beam the neutral axis does not pass through the centroid, so this will be r. So you can see this r is 4.480, and which is below from this centroid. So let this distance is capital R. I will write it over here. This capital R is equal to 4.4840 inch. Okay, now we will find, you can see we have find out this capital R, we have find out this R dash and R, clear? So we'll find this E. So E will be equal to R dash minus R. So R dash is how much? R dash is this 4.625 minus R is 4.480. So when you solve this, you will get this is equal to 0.1410 inch. Now each and every value is available except this R. This R, I have already told you that this is the distance from this center of curvature to the any point where you want to find the stress. It can be anywhere like this. And since we have been asked to determine the maximum bending stress in the beam, so maximum bending stress will either occur at this point or at this point. Let this point is point A and this point is point B. And you can see due to this movement, the beam will straighten up and this top portion will become in compression. Clear? This top, due to this movement, this upper one will be in compression and this bottom one will be in tension. Okay, now what we will do is that we have been given the bending moment. Clear? So just plug it in this formula. This is the formula. So for point A, what is point A? Point A is this A. So this distance will be equal to RA. This is your point A and this is your point B. So this is equal to RA. So first we will find the allowable bending stress for point A. So for point A, RA is equal to how much? RA is equal to 3 inch plus this 2 plus 0.5, which is 5.5. I will write R is 5.5 inch. And since point A is in compression, so I will write sigma A is equal to M into capital R minus RA divided by A into E into RA. So put the value, M is equal to how much? That is given as 40 pounds into feet. So we will convert this 40 pound into feet. In 40 multiplied by 12 will convert it into 40. 40 multiplied by 12 will convert it into pound into inch. So this is the value of movement. What is capital R? Capital R is 4.480 minus this RA. RA is 5.5 divided by area. Area is 2. What is E? So we have calculated E. Where is E? Where is E? E is here. This is E. This is E. So 0.1410 multiplied by RA is 5.5. So when you solve this, you will get stress, normal stress at point A come out to be 3 minus 314 psi. So this is equal to 314 psi, and it means that point A is in compression. Negative sign shows that point A is in compression. Now we will move toward finding the bending stress for point A, B. So bending stress for point B, which is in tension. So the formula sigma B will be equal to M multiplied by capital R minus RB divided by A into E multiplied by RB. What is RB? So RB is distance from center of curvature till this point B, which is equal to 3 inch. Clear? So I will write RB is equal to 3 inch. Rest all values are available. Moment was how much? 40 pound into feet. So 40 multiplied by 12 will convert the unit into pound into inch. Multiply by R. Capital R was 4.480 minus RB is 3 divided by area was 2. E was 0.1410 multiplied by RB is 3. So when you calculate it, you will get stress at point B comes out to be 842 psi. Since the value is positive, so it means that point B is in tension. Okay. So these are the answers of our this question. And that was all about this lengthy problem 6-139. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve example 8.4 that is taken from chapter number 8, Combined Loading, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the member shown in figure 8.5a has a rectangular cross section. Determine the state of stress at that loading produced at point C. So you can see this is the member that is having pin support at point A, and at point B there is a roller support, and there is a distributed load that is having magnitude 50 kilonewton per meter over a length of 2.5 meter. So the cross section is also shown. This is 50 by 250 millimeter rectangular cross section. So you have to determine the state of stress at point C due to this loading. So let's start with the solution. So first step is that if you remove this pin support at point A, so definitely you will be having a reaction force, horizontal reaction force. Let this is RAX, and similarly you will be having a vertical reaction force that will be equal to RAY. And same is the case when you remove this roller support at point B. So you will be having a reaction force that will be equal to RB. Okay, this will be RB. Now we will find this RAX, RAY and RB using equation of equilibrium. And you can see this length is 2 meter and this is 1.5 millimeter. So if I take this angle as theta, so you can say that theta is equal to tangent of theta is equal to perpendicular, which is 1.5 meter divided by base, that is 2, and theta will be equal to tan inverse 1.5 divided by 2, and when you calculate it you will get this theta will be equal to 36.86 degree. Now we will apply equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So what we will do is that you can see there is a distributed load 50 kilonewton. So when this distributed load is converted into point load, so this will be equal to 50 multiplied by the length over which it acts, that is 2.5. So we will get it 125 kilonewton. Now you can see that this member is making theta degree with the horizontal. Clear? So this will have this, I will resolve this it into rectangular component. This will be its vertical component and this will be its horizontal component. So you can see this member is making theta degree with this horizontal. So this line is perpendicular to this and its vertical line is perpendicular to this. So according to rule, the angle between them is theta. So the angle between these two will be also theta. So I will write here theta as well. So this component will be equal to 125 cos of theta, and this component will be equal to 125 sine of theta. Same is the case for RB. RB will have two components. One component along x direction, that will be this one. This will be equal to RBX, and other component will be vertical component, that will be RBY. So if I draw it like this, now you can see that this RB is perpendicular to this, and this vertical component is perpendicular to this. So if the angle between these two is theta, so this angle will be also theta. So I can write it here as theta. So this component will be equal to RB cos of theta, and this component will be RB sine of theta, this component. Now we have resolved all the forces into its components. So let's apply sum of all moment about point A is equal to 0. So you can see the first force that is producing moment about point A is this RB into perpendicular distance is 6, and that is producing counterclockwise movement. So it will be positive. So I can write it RB multiplied by RB into cos of theta. So theta is 36.86 degree into perpendicular distance is 6. The second moment is produced due to this force, which is, again you can see this will be RB into sine of 36.86, and perpendicular distance is 1.5, and this is also producing counterclockwise movement, so it will be positive. So I can write it RB into sine of 36.86 degree multiplied by 1.5. Now the another force that is producing moment is this one, and that is 125 into sine of theta, and theta is again 36.86. Since it is acting at the mid, so this distance will be equal to 1.5 divided by 2, which is 0.75, and this will produce clockwise movement, so it will be negative. So I can write it minus 125 into sine of 36.86 degree multiplied by 0.75, and the last force that is producing moment is this horizontal component, so it will act at this point. So 125 into cos of theta, and perpendicular distance is this one, so this will be half, which is 1 meter plus 4, and that is 5. So it is also producing clockwise, so it will be negative. So I can write it minus 125 into cos of, not sine, this will be cos of 36.86 degree multiplied by 5 is equal to 0. So this term will give us 4.8 RB. The second term will give us 0.89. The third term will give us minus 500, and fourth term will give us minus 56.23. That will be equal to 0. So it means that 4.8 RB, the second term is 0.89, and there is RB as well. Okay, plus 0.89 RB is equal to 556.23 kilonewton. So I will get 5.69 RB is equal to 556.23, and from here you will get RB will be equal to 97.75 kilonewton. Now we'll find this RAX and RAY by using another equation of equilibrium. So what is that? So I will write it. The equation of equilibrium that we will be using is sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see RAY, which is acting upward. So I will write RAY. This force, you can see this is acting downward. This is 125 cos of theta, and this is upward, plus RB into cos of theta. So I can write it minus 125 125 into cos of theta is 36.86 degree plus RB is 97.75 into cos of 36.86 degree is equal to 0. So when you solve this, you will get RAY will be equal to 21.80 kilonewton. Now last unknown reaction force is some RAX. So we will find that by using third equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So you can see RAX is acting positive, minus 125 sine of theta plus this RB sine of theta will be equal to 0. So I will write RAX minus 125 into sine of theta is 36.86 degree plus RB, which is 97.75 into sine of 36.86 degree is equal to 0. So when you solve this, you will get RAX will be equal to 16.34 kilonewton. Now you have all the reaction forces. So what we will do is that since we are interested to find out the rate of stress at point C, so you will cut the beam at point C and draw the free body diagram. So when you cut it at point C and draw the free body diagram, this is your point A where you have RAX, that is 16.34 kilonewton, and you have RAY, that is 21.80 kilonewton. This is point C. The distance between from A to C is given as 1.5 meter. You can see over here, clear. And when you cut it at point C, so you will be having a shear force V, you will be having a normal force N, and you will be having a moment M. Now we will find this V, M and N by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So 16.34 is toward positive minus this N is negative. Their sum must be equal to 0. So from this we will get N will be equal to 16.34 kilonewton. Okay. Now what we will do is that we will find this shear force by using this equation of equilibrium, and upward force is taken as positive. So N 21.80 is acting upward minus V is acting downward. Their sum must be equal to 0. So from here V will be equal to 21.80 kilonewton. And the last thing is movement. So we will find this movement by using equation of equilibrium, that sum of all movement about point C is equal to 0, taking the counterclockwise movement as positive. So about point C, one movement is due to this load, which is 21.80 into perpendicular distance is 1.5, that is acting clockwise, so it will be negative. Plus there is a reaction moment which is M, their sum must be equal to 0. So I will write plus M minus 21.80 into 1.5 is equal to 0. So from here we will get this moment will be equal to 32.8 kilonewton into meter. Now you have all this shear force, normal force, this is normal force, this is shear force, and this is moment at point C. So what we are going to do is that we will find the normal stresses due to normal force. So I will write it for normal force. First I will write it normal force causes normal stress, clear, and that can be obtained since it is asked to find at C. So sigma C is equal to minus N divided by A. Why minus? Because you can see this N is compressive. This is compressive stress towards C. So I can write it N is minus 16.34 kilonewton. So 3.4 into 10 raised to power 3 divided by area, cross-sectional area. So cross-sectional area is, this is breadth and this is height. So in meter it will be 0.05 and height will be 0.25. So I will write 0.05 multiply by 0.250. Okay. So when you solve this, you will get normal stress will be equal to 1.32 megapascal. That will be negative. But if you remove negative sign, so you can write that this stress is compressive. Okay. Now the second case is that you will have a shear force. So shear force, this vertical shear force causes shear stress. Clear? At point C. So we know that shear stress at point C is equal to V into QC divided by I into T. Clear? Since QC is equal to Y dash bar into A dash. So what is A dash? So A dash at this point, this is point C. So A dash about this point, there is no area. So it means that A dash is equal to 0. So I can write since A dash, since for point C, A dash is equal to 0. So it means that QC will be equal to 0. And when you put it in this formula, so you will get shear stress at point C will be 0. Okay. Now the third case is that bending moment, this bending moment M. So bending moment M causes bending stresses at C. And this bending stress, which is sigma C, is equal to M into minus M into Y divided by I. Clear? So what is M? M we have already calculated this. So bending stress will be equal to 32.8 into 10 raised to power 3. And what is Y? There is a negative side. Y is distance from neutral axis. So this is rectangular 250. So its neutral axis, our centroidal axis will be at the half. So this is 125 millimeter. So in meter, this will be equal to 0.125. So Y is equal to C. This is your point C. Clear? So I will write C will be equal to, Y will be equal to 0.125 divided by I. So for rectangular section, it will be equal to 1/12. Breadth is 0.05 and height is 250 millimeter, which is 0.250, and it will be cube. So when you solve this, you will get negative value, and that will be 63.16 megapascal. That will be negative, but if you remove it, negative sign, so it means that bending stress will be compressive. Clear? Now for case 1, if you want to draw the stress distribution, so let me draw it. This is the cross section. For example, if this is the portion of the beam. Okay. Now this is your point C. So at point C, due to normal stress, normal force, so the normal force will be like this one. This will be the normal force. So it will be like, the stress distribution will be like this. Since it is compressive, so you can see all the arrowhead will be toward this. So I can write over here that this is for normal stress. Next case is for shear stress. So again, I have to draw the figure like this. Clear? And we know that this is your point C. This is your point C. At C, shear stress will be equal to 0. But when you move downward, the shear stress will be in like this will be the shear flow. And we know that shear stress distribution in rectangular section is parabolic in this web portion. So I can say that at point C the shear stress is 0, but when you move down, shear stress increase and maximum at the centroidal or neutral axis. So this second case is about shear stress distribution in this rectangular section, and the third case is for the bending stress. So how we will do it, that let this is its neutral axis, here this is the beam, and we know that the above one was in compression, so I can write it like this will be the diagram, and below one is in tension. I will also show you how it will be in tension in compression. So you can see that this will be a straight line. Okay, so this all stresses will be in compression, and this will be in tension. This is your point C. Okay, so this third case is bending stresses. Now our all the combinations will give you the state of stress at point C. So you can see I will conclude it over here that we will use superposition, and what superposition says that since shear stress is 0 at point C and normal stress at point C is equal to the combination of this case 1 and 3. Clear? So I can write normal stress at point C is 1.32 megapascal and bending stress at point C is 63.16 megapascal. So total stress at point C is 64.5 megapascal. And this is the answer of our question. So if I want to draw it on the state of element like this, so you can see this will be sigma C. This element is taken at point C. There is sigma C, as there is no stress, shear stress at point C. So the stress at point C or state of stress at point C will be represented like this. And this was all about this example 8.4. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-140 that is taken from chapter number 6 bending, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. And the topic is curved beam. Statement is the curved beam is made from material having an allowable bending stress 24 KSI. Determine the maximum moment M that can be applied to the beam. You can see this is the curved beam, clear, and that is acted upon by a moment M, and the allowable bending stress is given as 24 KSI. So you have to determine this internal moment, largest value of this internal moment M that can be applied to this curved beam. So let's start with the solution. Here I have written the formula that is used in curved beam is the one is for the bending stress. E is equal to eccentricity, which is R dash minus R, and this capital R is equal to A over integral of dA over R for the entire area A. Now what is M? M is the moment, sigma is bending stress. What is capital R? So capital R is distance from this center of curvature till the point where its neutral axis lies. So this will be capital R. What is this R dash? So R dash is distance from this center of curvature to the point of centroid of this section. And remember, in curved beam, they do not lies in single points. Always this r dash or the distance from center of curvature till centroid is greater than this r. Clear? So we'll find this r and r dash first, and then we will solve this problem. So starting from this, I will first find this r dash. So r dash is equal to, it is distance, let me write it, distance from center of curvature till the point of neutral axis. No, it's the point of centroid, not neutral axis. Point of centroid. So where its centroid lies, so first we will find this r dash. So r dash will be equal to, for this T shape cross section, we know that its centroid will be equal to y dash into a divided by sum of area. So let this first rectangle is this one. This is your first rectangle. I will write it 1, and this is your second rectangle. So according to this, the formula will become y1 dash into a1 plus y2 dash into a2 divided by a1 plus a2. Now what is a1? So I will write it. You can see for this first rectangle, the a1 will be 2 into 0.5, which is equal to 1. So I will write 2 multiplied by 0.5, and that is equal to 1 square inch. Clear? What is a2? So a2 for this is area of a2, which is 2 multiplied by 0.5. Again 2 multiplied by 0.5, and that will give you 1 square inch. Now what is y1 dash? So y1 dash is distance from this centroidal axis. If I extend it, so this is the centroidal axis. So distance from centroidal axis till the mid of first section is y dash 1. So you can see this is y dash 1, and this distance is equal to this up till this distance. This is 3 inch. 3 inch plus 2 inch, 5 inch, and 0.5 divided by 2 is 0.25. So total distance will be equal to 5.25 inch. So I will write it 5.25 inch. So y1 dash is 5.25 inch. Now what is y2 dash? So y2 dash is distance from the center of curvature till the mid of second section. So this distance is equal to 2 divided by 1, and this will be y2 dash. Okay, so y2 dash will be equal to, it will be equal to, let me show you, this distance is 3 inch and this is 1. So this is 4 inch. So I will write 4 inch. 4 inch. Now you have all this value, just plug it in this formula. So you will get r dash, which is equal to 5.25 multiplied by area a1 is 1 plus y2 dash is 4 multiplied by area a2 is 1 divided by sum of area. So a1 is also 1 plus a2 is also 1. So when you solve this, you will get this r dash, which is equal to 4.625 inch, which is distance from this center of curvature till the centroid of this section. So let's say this distance is r dash. So I will remove these remaining things. This was for your understanding there. So I will represent this r dash first over here. So r dash, let's say this is the centroid C. This point is C, this point. So this distance was equal to, that we calculated, is r dash, and this r dash is equal to 4.625 inch. Okay, now what we will do is that we have find this r, we will find this r dash. r dash, we have find out this r dash, we will find this r, and we know that this r is equal to, this is the formula for r, area divided by integral of dA over r for the entire area. So area is equal to, we have already calculated total area. Area A is the total area of the cross section. So total area we have calculated is A1 plus A2. I will also write it so that you do not confuse. So this is 2 inch. Now what is this integral A dA over r? So for this we will have this table 6.1, where you, on the left side you have shape, and on the right side you have this term, formula for this term. So for rectangle this is this one, for triangle, for circle, and for elliptical shape. So here we have this rectangle shape. So this line shows you the axis passing through center of curvature. So from center of curvature, the base of the rectangle is r1, and the top layer is at a distance of r2. So here we have two rectangle 1 and 2. So first we will find this formula will become equal to sum of the two rectangle. Clear? So the first one here you can see for rectangle 2, its breadth is 0.5. Clear? And r1 will be, this is from, this is the centroidal center of curvature. So from center of curvature, this r1 is equal to 3 inch, and this r2 will be equal, this will be r2 for rectangle 2. So r2 will be equal to 3 plus 2, 5 inch. So this is 5 inch. So B is 0.5, r1 is 3, and r2 is 5 inch. So I will write, this is the formula. B is 0.5, clear, into ln of r2 was 5 divided by r1 was 3. Now we have the second rectangle is this one. So you can see this is the second rectangle. Its breadth is 2, and r1 for this first rectangle, sorry, this is first one. So this r1 will be equal to, you can see this will be 5 inch. This is r1, and r2 is this one from the center of curvature. So this r2 will be equal to 5.5. Clear? Up till this is 5, and 0.5 is 5.5. So I will write B was 2, and ln of 5.5, which is r2 divided by 5. Clear? So when you solve this term will give you the value 0.44633 inch. Now you have the area, you have this term, so just plug it in this formula. So R will be equal to 2 divided by 0.446033, and that's come out to be 4.4840 inch. And this R is distance from center of curvature till the point where its neutral axis lies. And you can see this is less than this R dash. So it means that your neutral axis is below somewhere. This neutral axis will be somewhere below this centroid of this section. So this is capital R. And this capital R we have calculated 4.4840 inch. Now you have this R dash and R, so you can just find E dash. So E is equal to R dash minus capital R. So R dash is 4.625 minus R is 4.4840. So when you calculate it, you will get 0.1410 inch. Now you have all these values. Since we have been asked to find the maximum allowable internal moment, so we know that bending stress will maximum at section AA either on this point or this point. Clear? So let this point is B point and this point is A point. So I will also designate them over here. This point is your B point and this point is let your A point. And you can see due to this bending moment, this point B will be in compression and this will be point A will be in tension, because it will cause, this movement will cause this beam to straighten up, causing this point B is in compression and A is in tension. So what we will do is that we will find the maximum bending moment for point A. Clear? As we know that this stress is equal, the formula for stress is equal to M into capital R minus R divided by A into E multiplied by R. Now what is R? I have already told you that R is distance from the center of curvature where you find the stress. So for point A, for example, for point A, we are interested to find out point A. So RA will be this distance. This distance will be RA. Clear? RA. So R will be replaced with RA. So R, I will write this as this. And this RA, you can see this is equal to 3 inch. 3 inch. So now you have all the values. The moment is given in the question, which is 24 ksi. So I will write this moment is 24 ksi, 24 into 10 raised to power 3 multiplied by capital R is this one, 4.480. Clear? This is 4.480. Let me check it. Allowable bending stress is given. This is allowable bending stress. Okay, not moment. Moment, we have to find the moment. So I will erase this. We need this moment M. So M multiplied by 4.480 minus RA, which is 3, divided by area, which is 2. E is, where is E? We have calculated E is this one. So 2 multiplied by 0.1410 multiplied by 3 is equal to this one. Since we know that bending stress is 24 ksi, so 24 into 10 raised to power 3 is equal to M into 4.480 minus 3 divided by 2 multiplied by 0.1410 multiplied by 3. And from here, you will get this moment will be equal to 24 into 10 raised to power 3 divided by 24 multiplied by 2 multiplied by 0.140 multiplied by 3 divided by this 4.480 minus 3. So when you solve this, you will get this moment comes out to be 13.68 kip into inch. Now this is the bending moment that is based on point A, which was Welcome back. In this video, we are going to solve example 8.6 that is taken from chapter number 8, Combined Loading, and book name is Mechanics of Material by R.C. Hibbeler, and its 9th edition. So statement of the problem is the solid rod shown in figure 8-7a has a radius of 0.75 inch. If it is subjected to the force of 800 pound, determine the state of stress at point A. So you can see this is a solid circular rod that is acted upon by a vertical force 800 pound in the direction of Z. Clear? So due to this load of 800 pound, you have to determine the state of stress at point A, that what are the stresses acting at point A. So let's start with the solution. So first step is that if you cut this rod at point A and draw the free body diagram, I have drawn it over here. So you can see that there is 800 pound that force is acting downward. Clear? So in order to balance this force at this point A, so there will be a vertical reaction force, or V will be equal to V will be applied in the direction of Z. And you can see that this 800 pound into perpendicular distance of 1400 will also produce a counterclockwise rotation at point Y, or about Y axis. So in order to balance it, we have a clockwise movement at point above y-axis, which will be my. So I will write it over here that here it will be having my. And due to this 800 pound into perpendicular distance is this one, which is 10 inch. So it is also producing clockwise movement in about x-axis. So in order to balance it, we must have anti-clockwise movement, which will be mx. So I will represent a movement about x-axis will be mx. Now we'll find this v, my and x by using equation of equilibrium. So first equation of equilibrium is sum of all forces along z direction must be equal to 0 and upward force is taken as positive. So v is acting upward, so v minus this 800 pound that is acting downward will be equal to 0. So it means that v is equal to 800 pound. Now we will find this my by using another equation of equilibrium, and that is sum of all movement about y-axis must be equal to 0, taking the counterclockwise movement as positive. So you can see my, which is acting clockwise, that is negative, multiply by 800 into perpendicular distance is 14, and this is producing counterclockwise movement. This will be positive and their sum must be equal to 0. So I can write minus my plus 800 into 14 is equal to 0. So it means that my will be equal to 800 into 14 will be equal to 11200 pounds into inch. So this is my. Similarly, we can find mx by using another equation of equilibrium, that is sum of all movement about x-axis must be equal to 0, taking the counterclockwise movement as positive. So above x-axis, mx is counterclockwise, which is reaction movement. So mx and about this x-axis, this perpendicular distance is 800 and this vertical force is 800 and perpendicular distance is 10 inch, and this is producing clockwise movement, so it will be negative. So I can write minus 800 multiplied by 10 is equal to 0. So from here we will get this mx will be equal to 8000 pounds into inch. Okay. Now we have seen that we have v is equal to 800 pound there, and my is 11200 pounds into inch, and mx is 8000 pounds into inch. So we will see that due to this vertical force at this cross section, we will be having shear force due to this movement my, which will produce torsion effect at this cross section, and due to this mx we will have a bending moment. So we will write these forces one by one. So starting from, I will write stress components. So starting with first one was what, shear force v. So shear force v will produce shear stress, and we will see that this shear stress will be equal to tau of yz. How? You can see that this is x-axis and this is z-axis. Here you can see x-axis and z-axis, and it is making y-plane. Clear? And tau of yz means that it will produce shear stress in this y-plane and in the direction of z. So this will be on this cross section, we will be having tau of yz. Okay. So we'll find this tau of yz. So we will see that this tau of yz is at, since we are finding it at point A, so tau of yz is equal to v into qa divided by I about x-axis, this shear force is vq divided by I into thickness t. Okay. Now what is v force? So you can see v is 800 pound. Clear? And what is qa? So for that I will, if I take this circle and draw the cross section over here, So if this is the circular rod, this is its x-axis and this is its z-axis. Clear? And this is your point A. So A lies on the centroidal axis or neutral axis. So we will take this area, this shaded area. So we know that y dash is equal QA is equal to y dash bar into A dash. So this will be A dash. Now what is y dash bar? So y dash bar is equal to, this is the formula, that y dash bar is equal to 4/3 pi into r, and A dash is equal to, it is semicircle, so it will be pi by 2 r power square, r square, pi by 2 r square. Okay, r square. So you have the value of r. So r is given as 0.75 inch. So I can write 4/3 pi into 0.75 multiply by pi by 2 into 0.75 whole square. Okay, whole square. Okay, now what we will get is QA. So put the value of QA, that will be 800, and from here if you calculate it, QA will be equal to 0.2813 inch power cube. Okay, so 0.2813 divided by, and I for this circular shaft will be equal to pi by 4 c power 4. Okay, so pi by 4 c power 4, c is 0.75 power 4 multiply by thickness. So you can see thickness will be this diameter, so that will be 2r. So multiply by 2 multiply by 0.75 inch. And when you solve this, you will get shear stress in y plane in the direction of z at point A comes out to be 604 psi, or you can say that shear stress in y plane in the direction of z at point A comes out to be 0.604 psi. So this is the shear stress due to the vertical shear force. Now we will calculate the bending stress, bending moment, which is mx produces bending stresses, bending stress, which will be equal to sigma in the direction of y. Clear? And we can find this sigma y will be equal to mx into y divided by mx into in the direction of z, because you can see this moment is this one and y is direction from the toward the z axis will cause to produce the stresses in y direction. So I can write it mx into z divided by ix into t, my divided by I. Bending stress is equal to my divided by I minus my divided by I, or you can see bending stress is equal to m into c divided by I. Since we are finding, you can see that this is the bending moment. Since we are finding the stress at point A, you can see point A is this one. So y is distance from neutral axis till top or bottom. So here this z value will be equal to 0 because A points lies on the neutral axis. So if you put z is equal to 0, so mx multiplied by 0 divided by I will give you 0 bending stress at point A. Rest, if you want to find the bending stress at top and bottom, it will not 0, it will having maximum value, but you can see that there will be a positive or negative value over here. Now what we will do is that we will third find the shear stress stress due to torsion, which will be due to this my, that is my. And we know that shear stress, this shear stress at point A will be again this will be y in the direction of z, and that will be equal to T into C divided by G, and here this moment will be equal to torque. Clear? So we can write T into C divided by J. So torque T or moment my is 11,200 pounds into inch. So 11,200 multiplied by C is distance from center till point A, which is radius. So we C is 0.75 divided by J. J is the polar moment of inertia, and for circular rod it is equal to pi by 2 C power 4. So C is 0.75 power 4. So when you calculate it, you will get it 16901 psi, or shear stress in the direction in y plane in the direction of z will be equal at point A will be equal to 16.90 ksi. Okay. Now you can see that all these shear forces or moments is on this portion, on this section. Clear? So if you take this section, so shear force here will be at this side will be downward, this movement will be in clockwise direction, and this will be counterclockwise direction, the opposite to which, for example, if this is the second section like this, so this shear force will be downward, this movement will be in counterclockwise, and this movement will be in clockwise direction. So if I draw this section like this, for example, if this is the circle, clear, and if I take it like this, so this is, for example, x-axis and this is z-axis. So shear force in the direction of z, this is z-axis, this is x-axis, so shear force will be in this direction. Clear? The moment about this x-axis will be clockwise, this will be mx, and moment about this y-axis, this is y-axis, so its moment will be in counterclockwise direction my. And now we will find that this is equal to, if you take only the vertical shear force along z direction, so its shear due to this vertical shear force, the stress distribution will be, this is your x-axis where you have point A and A dash. So due to this shear stress V, clear? So we have shear flow, and this shear flow will start from here, these points, and it will be maximum at point A. So this is the shear flow or shear stress due to only vertical shear force. So I can write shear force causes shear stress, and this shear stress is actually equal to 0.604 psi, tau of yz at A. Okay. Plus, if you take this bending stress, so what will be the stress distribution? So it will be like this. For example, this is the cross section, and if you have only this mx, so due to mx, this is the neutral axis A dash, A and A dash. So you can see that this stress will be maximum at this point. It will be, the top one will be in tension, clear, and bottom one will be in compression. And at neutral axis or at point A, the shear force will be equal to 0. So bending stress will be equal to 0. So sigma A will be equal to 0. And this is the stress distribution due to bending moment mx. And the last case is due to this my, which will cause torsional effect. So if I draw a circular section, so it will be like this, clear, and we can say that this is its A dash, A dash. And the shear stress, you can see here, it is like this on this section. Clear? So it will produce shear stress. So shear stress distribution, this is the center. So at point A, it will be maximum, and at center it will be equal to 0, because you can see if C is equal to 0, so shear stress at point C or center will be equal to 0. So this distribution will be like this one. Clear? Now what if I can write it, if you want to find the state of stress at point A, so what we will do is that we will use superposition. So what is superposition? So total shear stress in y plane, then direction of z at point A is due to this, which is 0.604, plus this stress, which is 116.90 KSI at point A, 116.90 KSI. So if you add them up, you will get the total shear stress at point A in y plane in the direction of z comes out to be 17.5 KSI. Clear? And if you want to have the representation of this shear stress on element at point A, so this stress will be like this. On top portion it will be like this, and same is the case for this. If you want to find the state of stress on element, differential element, so this stress distribution will be like this. It will be in downward direction. Clear? But overall state of stress on the element at point A will be equal to this one, which will be 17.5 KSI. The downward one will be the topward one. And this shear stress tau of YZ at point A comes out to be 17.5 KSI. So this was all about this example 8.6. I hope you have enjoyed this video and you have learning from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-138 that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. And the topic that we are covering here is curved beam. So statement is the curved member is made from material having allowable bending stress 100 megapascal. Determine the maximum allowable internal moment M that can be applied to the member. So you can see this is a curved member. Clear? And its allowable bending stress is 100 megapascal. So you have to determine the maximum internal moment that can be applied to this curved beam. So let's start with the solution. First of all, you should know about the formula that are used in curved beam. So first one is sigma is equal to M into R minus R divided by A into E multiplied by R. The second one is E is equal to R dash minus capital R, and the third one is R is equal to A over integral of dA over R for the entire area. So we will see them. What is this terms? So M is the moment. R, what is R? R is distance from this center of curvature to the point where its neutral axis lie. And what is this small r? So r can be any distance. It's distance from center of the curvature to the any point. It can be here, it can be here, it can be anywhere where you want to find the stress. And what is this r dash? So r dash is distance from center of curvature till the centroid of this section. So we will see them one by one. So let's start from finding r dash. So what is r dash? So r dash is distance from this center of curvature to the centroid of this. As we see that this is rectangular section, so its centroid will be in the mid of this. So if I take a horizontal line, So this point, at this point, this its centroid will be there, and distance from this center of curvature till this centroid of this curved beam is represented as r dash. So r dash is distance measured from the center of curvature to the centroid of this section. And this r dash, you can see this is equal to this radius of curvature is given as 200 millimeter. So 200 plus, you can see the half of this is 100 millimeter. Clear? So 100 plus 200 is 300. So this r dash will be equal to 300 millimeter, and that in meter it is 0.3 meter. So I will write r is equal to 0.3 meter. Next term that we will find is capital R. And what is capital R? So capital R is distance from the center of this curvature till the point where its neutral axis lie. So we will find this R. So R is equal to A over integral of dA divided by R for the entire area. So first we will find this area. So what is area? So you can see the cross section is given over here. This is 100 by 200 millimeter. So in meter it will be so area of rectangle is breadth multiplied by height. So breadth is 0.1 meter and height is 0.2 meter, and the unit will be square meter. So this is area, and now we will find this term which is integral of dA over R for the entire area. So for this we will use the table that is shown over here. You can see you have shape in the first column and integral of dA over R for the entire area. The formula is given. So here we have this rectangular shape. Clear? And we also have here the rectangular shape. So what we will do is that this line represents the axis passing through center of curvature. So from center of curvature, the base of this rectangle is R1 and the upper one is R2. So we will locate. So you can see this is the, if I draw a horizontal line from the center of curvature, clear, axis of center of curvature. So this first distance which we represented as R1 will be equal to how much? It will be equal to this 200, it will be equal to 0.2 meter. And another distance from this axis of center of curvature till the outer layer is represented as R2. So it will be, R2 will be this one. And you can see this distance is 0.2, and this is also 200 millimeter, which is 0.2. So R2 will be equal to 0.4. And the formula that we will use for here will be equal to, this will be equal to breadth time ln of R2 over R1. So what is breadth? So you can see the breadth is 100 millimeter, which is equal to 0.1. And what is, we will write ln of, what is R2? So R2 is 0.4 divided by 0.2. Okay. So this will give you this term. Now put these two values in this formula. R is equal to A divided by integral of dA over R for the entire area A. So area is equal to 0.1 multiplied by 0.2 divided by this value, which is 0.1 multiplied by ln of 0.4 divided by 0.2. So when you calculate it, you will get this capital R, and this capital R comes out to be 0.288539 meter. So we will represent it on the diagram. So this R will be equal to distance from neutral axis till the centroid, till the point of location of neutral axis. So this is 0.3, as it is less than 0.3. So this will be the point. Clear? And this distance from this till this point, this will be equal to this point. This will be equal to capital R. And this capital R is equal to 0.288539 meter. Okay. Now you have all these values. So we will find this E over here, and we know that E is equal to, I have written over here, this E is equal to R dash minus R. So R dash is how much? You can see this is 0.3. So 0.3 minus 0.2888539 meter. And when you calculate it, this E will be equal to 0.011461 meter. Now we are interested to calculate the maximum allowable internal movement. So we know that maximum bending moment occur at this top or bottom surface. So you can see that due to this movement will cause this curved beam to be flattened. Clear? So the upper portion, this portion will be in tension and the lower portion will become in compression. Clear? So what we will do is that we will designate these points. This is point A and this is point B, and I will also represent it over here, A and B. So we will find the moment. We will apply the bending stress formula, this one, for both points A and B in order to determine the maximum allowable bending stress. So I will write allowable bending stress. So for point A, first we will find for point A, so which is in tension, So the formula or maximum stress or allowable stress at point A, this formula will become M into capital R. And what is small r? So small r is distance from center of curvature to anywhere where you want to find the stress. Since we are interested to find out the stress at this point, so this will be equal to RA, which is equal to 200 millimeter or 0.2. So I will write RA divided by area into E multiplied by RA. Now put the value, we will put the value in this equation. Okay, so allowable stress is given as how much? It is given as 100 megapascal. So I will write 100 into 10 raised to power 6, will convert it into pascal. And this moment which is not known, and we are interested to find out this moment, M and R is capital R is 0.288539 minus RA. So RA, I have told you that this RA was this distance, which is equal to 0.2 meter. So I will write minus 0.2 divided by area. Area is 0.1 multiplied by 0.2 from the cross section. Clear? And what is E? So E is equal to this one, 0.011461 multiplied by RA. RA is 0.2. So when you solve this for M, so this moment M will be equal to 100 multiplied by 10 raised to power 6 multiplied by 0.1 multiplied by 0.2 multiplied by 0.011461 multiplied by 0.2, and that is divided by 0.288539 minus 0.2. So when you solve this, you will get the maximum allowable bending moment for point R. For point A comes out to be 51778.27 Newton meter, and this in kilonewton meter, it is equal to 51.8 kilonewton into meter. So this is the value of bending, allowable bending moment for point A. Now we will move toward point B. For point B, which is in compression. I have already shown you, and I will again show you that this point B, you can see due to this movement, this point B will be in compression. So this allowable bending stress will be negative. So I will write again, the formula will be equal to allowable stress will be equal to M into R minus, for RB we are finding this divided by A into E into RB. So allowable bending stress is 100 megapascal. So at point B it is in compression. So I will write minus 100 into 10 raised to power 6. The moment is there, not available. We are interested to find out this moment. So moment into capital R, which is 0.288539 minus RB. What is RB? So RB is distance from the center of curvature till point B. So this distance is 200 and this distance is also, you can see this is 200. So total is 400 millimeters. So in meter it is 0.4. So I will write minus 0.4 divided by area. Area is 0.1 multiplied by 0.2 into E. E is 0.011461 multiplied by this RB. RB is 0.4. So from here you will get this moment will be equal to minus 100 into 10 raised to power 6 multiplied by 0.1 multiplied by 0.2 multiplied by 0.011461 multiplied by 0.4 divide by this term, which is 0.288539 minus 0.4. So when you solve this, you will get the value of moment comes out to be 822610.26. Let me correct it. This is 8226.10 Newton meter, and in kilonewton meter it is equal to 82.260 kilonewton into meter. Now this is the value of bending moment, maximum allowable bending moment for point B. So you have two values, one is this one and another one is this one. So what we will do is that we will choose the smallest one because it will be the safer. It will not exceed the maximum allowable bending stress at both the points. So my answer is that choose M is equal to 51.8 kilonewton into meter, which is the answer of our this question. And that was all about this problem 6-138. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-141 that is taken from chapter number 6 bending, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So topic is curved beam. Statement is if P is equal to 3 kilonewton, determine the bending stress developed at point A, B and C of the cross section at section AA. Using this result, sketch the stress distribution on section AA. So you can see this is a curved beam that is acted upon by this load P, which is given as 3 kilonewton. So at section AA, you have to determine the bending stress at point A, B and C. And after finding this, you have to determine the stress distribution on section AA. When you section it, the cross section is shown over here. So let's start with the solution. The formula that we will use in this curved beam is this one. This is the formula for bending stress, where you have M, which is moment, capital R minus small r. So small r is distance. You can see this is a curved beam, so its radius of curvature is given as 300 millimeter. So this is center of curvature. So capital R is distance from center of curvature till the point where its neutral axis lies. And what is this small r? So small r is distance from this center of curvature to every point where you want to find the stress. Just like here, you can see we have to find the stress at point A. So it will be RA. At point B, it will be RB. And at point C, it will be RC. Clear? And R dash is distance from the center of curvature till the centroid of this section. So let's start with the solution. What will be the first step is that if you cut this curved beam at section AA and draw the free body diagram I have drawn over here. So you will see you will having a shear force V at section AA which will act upward. So it will be VA dash A, and you will be having a moment in clockwise direction. This is equal to MAA. So we'll find this moment because this internal moment will cause bending effect. So we'll find this by using equation of equilibrium, that sum of all moments about neutral axis is equal to 0, and taking the counterclockwise moment as positive. So you can see the first moment is due to this P load, and perpendicular distance is this 0.6 meter or 600 millimeter. Clear? And that is producing counterclockwise effect, so it will be positive. So I will write P into 0.6. The second moment at this neutral axis will be this moment MAA dash, that is clockwise, so it will be MAA. Their sum must be equal to 0. So from here, this moment MAA will be equal to 0.6 times P. Now you know the value of P, that is given as 3 kilonewton. So just put it 0.6 into 3 kilonewton will give you 1.8, and the unit will be kilonewton into meter. This is moment at point AA. Okay, now you have this moment. So you can see that due to this moment that is acting like this, and due to this load the moment will act like this. So it will produce bending effect. So I will draw it over here. Here the moment is like this, and due to this load the moment is like this. So it will cause this bending in this curved beam, and it will try to straighten this curved beam. So the top, these two portions will be in tension, while this point C will be in compression, because the top layer is going to stretch while the bottom layer is compressed. So C is in compression while A and B is in tension. So we'll find them one by one. So we have this moment M. So by using this formula you can see we have find out the M. Now we will find this capital R, and you can see we have another term E, which is equal to R dash minus R. What is R dash? So R dash is distance from this center of curvature to the centroid. So we will find this R dash first. So R dash is equal to, let me write it, distance from center of curvature to the centroid of section. Okay, as we know that we have this section, so you can see this is T shape. So if I draw a horizontal line from this center of curvature, and you can see this is T section, so we divide it into two portions. The first one is this one, and the second one is this one. So we know that its centroid can be obtained by using this formula, which is equal to R dash will be equal to Y1 dash into A1 plus Y2 dash into A2 divided by sum of area, which is A1 plus A2. Now what is A1? So A1, you can see this is 20, this is, the thickness is 20 millimeter. This thickness is 20 millimeter, and this width is 75, because 25 plus 25 plus 25 is 75. So I can write A1 is 20 divided by 1000 will give you in meters. So 0.02 multiply by 0.075 meter. Similarly, you can see A2 is equal to, let me zoom it. You can see A2 is, area 2 is 25 millimeter by 50 millimeter. So I will convert them into meter. Clear? Okay. So AT is 0.025 meter multiplied by 0.05 meter. and then unit will be square meter, and here it will be also square meter. Now what is y1 dash and y2 dash? So y1 dash is distance from this center of center of curvature to the mid of first section. So this is the mid of first section. So you can see that this distance from centroid curvature is 300 millimeter, and half of 20 is 10. So this will be equal to 310 millimeter. So I will write this will be y1 dash, and y1 dash will be equal to 310 millimeter, or that is equal to 0.310. What is y2 dash? So y2 dash is distance from center of curvature till the centroid of second section. So this is y2 dash. Let me write it first, y2 dash. And y2 dash, you can see that this will be equal to 300 plus 10 is 310, and the half of 25 is 310 plus 25 is 330, 340, 335. Okay, no. 30 up till now, this plus 20 is 320, and 25 is this, so 345. So I will write y2 dash is equal to 345 millimeter. So I will write them downward. Clear? Okay. So y1 dash is equal to 0.310 meter, and y2 dash is equal to 0.345 meter. Now you have all the value, you can just plug it in this formula. So y1 dash is 0.310 multiplied by area 0.02 into 0.075 plus our y2 dash 0.345 into A2, which is 0.025 multiplied by 0.05 divided by the area A1 and A2. So you can see A1 is 0.025, sorry, 0.02 multiplied by 0.075 plus A2 is 0.025 multiplied by 0.05. Okay, so when you solve this, you will get R dash comes out to be 0.325909 meter. So it is basically the distance between center of curvature till the centroid of first section. So let me delete these things. You have now a clear understanding. So we found out that distance from this is the centroid, which is C. So distance from the center of curvature till the centroid is R dash. Clear? R dash. So we have find out this R dash comes out to be 0.325909 meter. Okay, so what we will find is that we have find out this one. So we will find this R, and R is equal to, you can see you have this formula. So I will write it. R is equal to area divided by integral of dA over R over area A. And as we know that area, I will choose another color, area is equal to, total area is equal to A1 plus A2. So A1 is 0.02 multiplied by 0.075 plus A2 is 0.025 multiplied by 0.05. Okay, so when you solve this, you will get this area, total area comes out to be 2.75 into 10 raised to power minus 3 unit will be square meter. Now what about this term that is given in denominator, which is integral of dA over R for the entire area? So you can see we can find this by using this table 6.1. Here there are shapes and their formula for integral of dA over R for the entire area. Since you can see we have two portion, 1 and 2, and both are rectangle. So what we will do is that we will use this formula. So formula for this. So now this is the line which is passing through the center of the curvature. So you can see from the center of curvature, the first side or first portion of this rectangle is at a distance of R1, and second one is at a distance of r2, and the width of this rectangle is b. So we will take these values over here. You can see that for the first, this is the breadth, which is total 75, clear, and this will be r1. R1 will be how much? It will be 0.3 meter. And what is R2? So R2 is distance from center of curvature till the second portion of the rectangle. So total will be 20 plus 300 is 320. So breadth is 75. So I will write it is equal to breadth is 75. So which is 0.075, clear. And the formula here is this one, B into ln of R2 or R1. So B is 0.075, ln of R2 was 0.32 divided by R1 was 0.3, clear? Plus, now we have another rectangle, this rectangle. So you can see R1 will be this one, this will be R1, which will be equal to 320 millimeter or 0.320, and R2 will be distance from this center of the curvature till this. So this total height is 50 plus 20 plus 300 is 370. So R2 will be 0.370. And what is the width or breadth? So it is 25 millimeter. So I will write it. 25 millimeter is 0.025 into ln of R2 or R1. So R2 was 0.37, clear, divided by R1. R1 will be, R1 was 0.32. Okay. So when you solve this, you will get integral of dA over R for the entire area comes out to be 8.46994 into 10 to the power minus 3. Now you have the value of A and this integral, so just plug it in this formula. So I will write it 2.75 into 10 to the power minus 3 divided by 8.4699 into 10 to the power minus 3. Okay. So when you solve this, you will get this R will be equal to 0.324678 meter. And what is this R? R is distance from centroid of the, center of curvature till the neutral axis. So as R is less than this, so it will be somewhere here. It will be somewhere here. This will be your R, capital R. Okay. Now we have these values, both values, E and E, this value. So E will be equal to R dash. R dash is how much? We have calculated R dash is this one. So 0.325909 minus capital R is 0.324678. So when you calculate it, you will get this E will be equal to 1.2314 into 10 to the power minus 3, and the unit will be meter. Now you have all these things, so just put it in this formula. I will write the formula downward or on next page. So formula for stress is equal to M into capital R minus R divided by AE into R. Okay, number one, for point A, the stress for point A. So R will be equal to RA. And you can see that at point A, the R will be, this is point A. You can see this is point A. So R will be 300 millimeter. So I will write, put R is equal to 300 millimeter or 0.3 meter. And put the value. So sigma A will be equal to what was the value of moment that we calculated, if you remember, 1.8 kilonewton. This is the value, 1.8 kilonewton. So 1.8 into kilo is 10 to the power 3 multiplied by capital R was 0.324678 4678 minus RA is 0.3 divide by area. So area we calculated was 2.75 into 10 raised to power minus 3 multiply by this E, which is 1.2314 into 10 raised to power minus 3, and RA is 0.3. Okay, so when you calculate it, you will get bending stress at point A comes out to be 43.7 megapascal. So the value is plus that. It means that point A is in tension. Okay, we will move towards second part. So that is for point B, stress for point B. So at point B, we have R is equal to RB, and let me show you that RB is at this distance. So this is 300 plus this thickness was 20. So 320 millimeter R, that will be equal to 0.320. So put it in this formula, you will get stress at point B is equal to moment into R minus RB divided by area E into RB. So put the value, M is 1 into 10 raised to power 1.8 into 10 raised to power 3 multiply by R is 0.324678 minus RB is 0.320 divided by area, which is 2.75 into 10 raised to power minus 3 multiply by E, which is 1.2314 into 10 raised to power minus 3 multiply by RB is 0.320. So when you solve this, you will get stress at point B comes out to be 7.77 megapascal. And this value is also positive, so it means that point B will be in tension. Okay. The last part is that we have to find the stress, bending stress at point C. So for point C, R will be equal to RC, and you can see that RC is this distance from top till the end. So this total distance is 300 plus 20 plus 50, so 370. So RC is equal to 370, which is equal to 0.370. Okay, so again put it in this above formula. So sigma C will be equal to M is 1.8 into 10 raised to power 3 multiply by capital R is 0.324678 minus RC is 0.370 divided by area, which is 2.75 into 10 raised to power minus 3 multiply by E, 1.2314 into 10 raised to power minus 3 multiply by 0.370. So when you solve this, you will get this stress comes out to be negative, because this value will give you minus. So this will be equal to minus 65.1 megapascal. Or you can also write it that sigma C is 65.1 megapascal, and instead of negative you can write that point C is in compression. Okay. Now you have all these values. So this is the answer of our first part. In second part, we have been asked to determine the sketch distribution on section AA. So what if I draw section AA like this? For example, if this is the beam, clear. So when you cut it and draw it like this, so I will take this initial section is like, and this will be curved like this. Let this is its neutral axis. At this point it has a neutral axis. This is your point A, this is your point B, and this is your point C. So at A we have 43.7 megapascal. So it will be like this. Let this is 43.7 megapascal. And at neutral axis we have 0, and it will be like a parabolic curve. It will be like this. Okay, at point B we will have 7.77 megapascal, and till neutral point it will become 0. Now at C we have a compression, so you can see at point C this is equal to 65.1 megapascal, that is in compression side. So this curve will be like this. It will be like this. Okay. So this is the stress distribution along section AA. This was section AA. And that was all about this problem 6-141. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.